Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration, a calm lecture into the most profound and captivating mysteries that science has yet to unravel. We will drift through the cosmos, delve into the deepest reaches of the mind, and ponder the fundamental questions that have echoed through human history. Prepare to be soothed by the sheer wonder of the unknown, to find a quiet perspective in the vastness of our ignorance, and to allow the majesty of these unsolved questions to lull you into a peaceful slumber. Let us begin our journey into the biggest unsolved questions in science. The universe's darkest secret is not what you think. For eons, humanity has gazed upwards, seeking answers in the celestial tapestry. We've marveled at the distant gleam of stars, the majestic swirl of galaxies, and the silent dance of planets. Yet, beneath this breathtaking spectacle lies a profound and humbling truth. The vast majority of the universe is utterly invisible to us, composed of substances we cannot directly detect or comprehend. This unseen realm, often referred to as dark matter and dark energy, constitutes approximately 95% of the cosmos. The remaining 5%, the stars, the planets, the nebulae, and ourselves, are merely a fleeting, luminous whisper in an ocean of cosmic darkness. This isn't a secret born of conspiracy or hidden knowledge, but rather a fundamental limit of our current scientific understanding. It is a testament to the universe's immense scale and complexity that so much of its essence remains shrouded in mystery. Our telescopes, our most advanced instruments, can only perceive a fraction of what exists. The gravitational influence of dark matter, for instance, is undeniable. Galaxies rotate far too quickly to remain intact if only the visible matter were present. The stars on the outer edges of galaxies would be flung outwards, tearing these celestial islands apart. Yet they hold together, a silent testament to an unseen scaffolding of mass that binds them. Similarly, dark energy is the driving force behind the accelerating expansion of the universe. Galaxies are not just moving away from each other. Their recession is speeding up, as if an invisible hand is pushing them further apart with ever-increasing force. This phenomenon challenges our very understanding of gravity, the force we once believed would eventually slow down the cosmic expansion due to the mutual attraction of all matter. The implications of this unseen majority are staggering. It suggests that our familiar laws of physics, while remarkably successful in describing the visible universe, may be incomplete or even fundamentally flawed when applied to the grander cosmic scale. We are like inhabitants of a single, tiny island, meticulously charting the shores and currents of our immediate surroundings, while the true immensity of the ocean, with its deep abysses and unseen life, remains largely beyond our grasp. The quest to understand dark matter and dark energy is one of the most pressing and exciting frontiers in modern cosmology. Scientists are devising ingenious experiments, both on Earth and in space, to detect the elusive particles of dark matter, perhaps through their rare interactions with ordinary matter, or by searching for the subtle decay products they might produce. The nature of dark energy is even more enigmatic. Is it a constant property of space itself, a vacuum energy that permeates the cosmos? Or is it a dynamic field that changes over time and space? The answers to these questions will undoubtedly revolutionize our understanding of physics and our place within the grand cosmic architecture. It is a profound realization that our perception, our senses, and our current scientific frameworks are limited. The universe, in its infinite wisdom, has presented us with a challenge, a cosmic riddle that pushes the boundaries of human intellect and curiosity. This unseen majority is not a source of fear, but rather an invitation to wonder, to ponder the vastness of the unknown, and to appreciate the profound beauty of what we can perceive. knowing that it is but a small part of a much grander, more mysterious reality. The darkness of the universe is not a void, but a canvas upon which its most profound secrets are painted, waiting patiently for our discovery, inviting us to dream bigger, to question deeper, and to embrace the magnificent, unresolved mysteries that surround us, urging us towards a deeper, more peaceful understanding of our own place within this grand cosmic narrative. In the silent expanse, the unseen holds the universe in its gentle, mysterious embrace. We don't know what 95% of the universe is made of. Imagine for a moment standing on a clear night, gazing up at the countless stars. It's a breathtaking spectacle, a vast expanse of light and wonder that has captivated humanity for millennia. We've learned so much about the cosmos, deciphering the whispers of distant galaxies, understanding the life cycles of stars, and mapping the intricate dance of planets. Yet, as our telescopes and scientific instruments become ever more sophisticated, a profound and humbling truth emerges. All that we can see, all that we can directly observe and interact with, accounts for only a tiny fraction of the universe's true composition. The vast majority, a staggering 95%, remains shrouded in mystery, composed of substances we cannot directly detect, and whose fundamental nature eludes our current understanding. This is the realm of dark matter and dark energy, two of the most significant and persistent enigmas in modern cosmology. Let's begin with dark matter. When astronomers observe galaxies, they see stars, gas, and dust rotating around a central point. Based on the visible matter present, we can calculate how fast these components should be moving due to gravity. However, observations consistently reveal that galaxies are rotating much faster than predicted. Stars on the outer edges of galaxies are moving at speeds that should, by all accounts, cause them to be flung out into the intergalactic void. Yet they remain firmly bound. This discrepancy suggests that there must be a significant amount of additional mass, an invisible gravitational anchor, holding these galaxies together. This unseen mass is what we call dark matter. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes across the entire electromagnetic spectrum, from radio waves to gamma rays. It's as if the universe is populated by ghosts, their gravitational influence undeniable, but their physical form utterly elusive. The evidence for dark matter isn't confined to galactic rotation. It's also inferred from the way light bends around massive objects, a phenomenon known as gravitational lensing. When light from distant galaxies passes through clusters of galaxies, its path is distorted, much like light passing through a lens. The degree of this bending is directly proportional to the mass of the intervening object. Again, the observed lensing effects are far stronger than what can be accounted for by the visible matter alone, pointing to the presence of substantial amounts of dark matter. Furthermore, the cosmic microwave background radiation, the faint afterglow of the Big Bang, also carries imprints of dark matter's influence on the early universe. Without dark matter, the structure of the universe as we see it today, the formation of galaxies and galaxy clusters, simply wouldn't have occurred in the way it has. So if dark matter is so pervasive and its gravitational effects so significant, what could it be? This is where the mystery deepens. The leading candidates for dark matter are hypothetical particles that interact very weakly with ordinary matter, aside from through gravity. These are often referred to as weakly interacting massive particles, or WIMPs. These particles are not part of the standard model of particle physics, which describes all the known fundamental particles and forces. This means that if WIMPs exist, they represent entirely new physics, a discovery that would revolutionize our understanding of the universe. Scientists are actively searching for these elusive particles using highly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch a rare interaction between a WIMP and an atom in their detector. Other theories propose alternative candidates, such as axions or even modifications to our understanding of gravity itself, though these remain less favored. The truth is, we simply don't know. Now, let's turn our attention to dark energy. While dark matter acts as a cosmic glue, holding structures together, dark energy is something far stranger. It appears to be an invisible force that is causing the expansion of the universe to accelerate. For decades, scientists believed that the gravitational pull of all the matter in the universe would be gradually slowing down its expansion. However, observations of distant supernovae in the late 1990s revealed a startling truth. The universe isn't just expanding, it's expanding at an ever-increasing rate. This acceleration is attributed to dark energy, a mysterious force that seems to be inherent to space itself. It's as if the fabric of space-time has a built-in repulsive property, pushing everything further apart. The nature of dark energy is even more perplexing than that of dark matter. The simplest explanation is that it's a cosmological constant, a fundamental energy density inherent to the vacuum of space, as proposed by Albert Einstein in his theory of general relativity. However, theoretical calculations of this vacuum energy yield a value that is astronomically larger than what is observed, a discrepancy of about 120 orders of magnitude, the largest fine-tuning problem in physics. Other possibilities include a dynamic energy field, sometimes called quintessence, that changes over time and space, or perhaps our understanding of gravity itself needs to be revised on cosmic scales. Whatever it is, dark energy constitutes about 68% of the total mass energy content of the universe, a dominant force shaping its ultimate destiny. The implications of this cosmic ignorance are profound. It means that the universe we inhabit, the one we can observe and study directly, is merely a thin veneer over a vast, unseen reality. The stars, planets, and galaxies that fill our cosmic panorama are like the foam on a deep, dark ocean, its true depths largely unexplored. This isn't a failure of science, but rather a testament to its power. It's in confronting these profound unknowns that science truly shines, pushing the boundaries of human knowledge and sparking our deepest sense of wonder. The quest to understand dark matter and dark energy is not just about filling in the blanks. It's about fundamentally redefining our place in the cosmos and unraveling the deepest secrets of existence itself. It's a reminder that even in our most advanced explorations, the universe retains an immense capacity for surprise, for mystery, and for awe. And in this grand cosmic mystery, we too are a part of the unseen, a confluence of elements forged in stars, now contemplating the very fabric of the universe that birthed us, finding peace in the vastness of what we do not yet know. The beginning of everything remains a cosmic enigma. The grand tapestry of existence, stretching across billions of years and incomprehensible distances, begins with a question that echoes through the very fabric of space and time. What was there before the Big Bang? Our current understanding of cosmology, the study of the universe's origin and evolution, points to a singularity, an infinitely dense and hot point from which all matter, energy, space, and time originated. This is the cornerstone of the Big Bang theory, a model that has been overwhelmingly supported by observational evidence, such as the cosmic microwave background radiation and the expansion of the universe. However, the singularity itself presents a profound conceptual hurdle. It represents a point where our current laws of physics, particularly general relativity, break down. We cannot, with our present theoretical frameworks, describe what existed at asterisk or before this infinitesimally small, infinitely energetic moment. The Big Bang theory describes the asterisk evolution of the universe from a very early, hot, and dense state. It tells us how the universe expanded, cooled, and how structures like galaxies and stars eventually formed. But it doesn't, or rather can't explain the initial conditions themselves. It's akin to finding a magnificent, intricate clockwork mechanism and understanding how each gear turns and interacts, but having no idea who built it or where the raw materials for its creation came from. The very concept of before becomes problematic when we consider that time itself is thought to have begun with the Big Bang. If time is a dimension that emerged with the universe, then asking what happened before is like asking what is north of the North Pole. The question itself may not have a meaningful answer within our current understanding of reality. This is where theoretical physics ventures into speculative, yet deeply fascinating territories. Some cosmological models propose ideas like cyclic universes, where the Big Bang is not a singular beginning, but rather one event in an endless cycle of expansion and contraction. In such scenarios, a previous universe might have collapsed, leading to a bounce that initiated our current expansion. Other theories explore concepts like quantum fluctuations in a pre-existing vacuum state, suggesting that our universe could have spontaneously arisen from a state of nothingness, a state that itself is not truly nothing, but rather a quantum field with potential energy. The idea of a multiverse also enters the picture, proposing that our universe might be just one bubble among countless others, each with its own unique set of physical laws and initial conditions. These ideas, while not yet directly observable, are attempts to push the boundaries of our knowledge and address the fundamental enigma of origins. The challenge lies in the fact that any event before the Big Bang, if such a concept is even valid, would be beyond our causal reach and potentially beyond any form of observation. The information from such an epoch would have been obliterated by the immense energies of the Big Bang itself. So, while we can trace the universe's history back with remarkable precision to fractions of a second after its inception, the absolute genesis, the very spark of existence, remains shrouded in a mystery that ignites the deepest curiosity within us. It's a frontier not of space, but of fundamental understanding, a testament to the vastness of what we don't yet know about the very beginning of everything we do know. And so, the dawn of existence, a moment both impossibly distant and intimately connected to our present, remains a whisper in the cosmic dark, reminding us that the grandest of stories often begin with the most profound of questions. The nature of time itself eludes our full grasp. We often perceive time as a river, a steady, unidirectional flow from past to future. We mark its passage with clocks, calendars, and the changing seasons. Yet, when we delve into the profound depths of physics, this seemingly simple concept begins to unravel into something far more intricate and, frankly, quite mysterious. Einstein's theories of relativity, particularly general relativity, revolutionized our understanding of time, revealing it not as an absolute, universal constant, but as something intimately interwoven with space, forming a four-dimensional fabric known as spacetime. This fabric, we now understand, is not static but dynamic, capable of being warped and stretched by mass and energy. One of the most mind-bending implications of this is time dilation. Imagine two identical clocks perfectly synchronized. If one clock is placed in a stronger gravitational field, say, closer to a massive object like a planet or a black hole, or if it travels at a significant fraction of the speed of light, it will tick slower than the other clock. This isn't a malfunction, it's a fundamental property of space-time. The stronger the gravity, or the faster the motion, the more time itself stretches. This means that time is not the same for everyone, everywhere. Your experience of time is relative to your motion and your gravitational environment. This has tangible consequences, even in our everyday lives. The GPS satellites that guide us rely on incredibly precise atomic clocks. These clocks experience both time dilation due to their speed and a slight time acceleration due to being in a weaker gravitational field than we are on Earth's surface. Without accounting for these relativistic effects, GPS systems would quickly become inaccurate, drifting by kilometers each day. But the mysteries don't end there. The arrow of time, why it seems to flow only forward, is another profound puzzle. While the fundamental laws of physics at the microscopic level are largely time-symmetric, meaning they work the same forwards and backwards, our macroscopic world clearly exhibits a direction. We remember the past, not the future. Eggs break, but they don't spontaneously reassemble. This unidirectional nature of time is often linked to the second law of thermodynamics, which states that the entropy, or disorder, of a closed system always increases. As the universe evolves, it moves towards a state of greater disorder, and this increase in entropy seems to define the forward march of time. Yet, the ultimate reason for this asymmetry, and why the universe began in a state of such low entropy, remains a subject of intense debate and speculation. Furthermore, the very concept of the present becomes fuzzy when we consider the finite speed of light. When you look at a star, you are not seeing it as it is now asterisk, but as it was when its light left it, perhaps millions or even billions of years ago. The light from the sun takes about 8 minutes to reach us. So, when you look at the sun, you are seeing a version of it that existed 8 minutes in the past. This means that our perception of simultaneity, of events happening at the exact same moment, is also relative. Two observers moving at different speeds might disagree on whether two distant events occurred at the same time, or which one happened first. The quantum realm introduces even stranger possibilities. Some interpretations of quantum mechanics suggest that time might not be fundamental, but rather an emergent property, arising from deeper, timeless principles. The idea of a block universe also emerges from relativity, suggesting that all of time, past, present, and future, exists simultaneously, and our perception of it flowing is an illusion of consciousness. This challenges our very intuition about free will and the unfolding of events. The philosophical implications are staggering. If time is not a fixed, universal constant but a fluid, malleable dimension, then our understanding of causality, destiny, and existence itself is profoundly altered. Are we merely observers experiencing a pre-written cosmic narrative, or do our actions truly shape the unfolding of moments? The questions about time are not just abstract scientific curiosities. They touch upon the very essence of our lived experience and our place within the grand tapestry of the cosmos. The intricate dance between space and time, the relentless increase of entropy, and the subjective nature of our perception all contribute to the enduring enigma that is time. And so, the river of time, once so clear, flows into a sea of profound questions, reminding us of the vastness of what we do not yet comprehend. Consciousness, the most intimate mystery of all. Our journey through the grand tapestry of the cosmos, the intricate dance of subatomic particles, and the vast, silent expanse of the universe, inevitably brings us to a mystery that resides not in the distant stars, but within the very core of our being. It is the enigma of consciousness, the subjective experience of being, the inner world of thoughts, feelings, and perceptions that defines our existence. This is perhaps the most intimate and profound puzzle science has yet to fully unravel. We understand with remarkable clarity the physical mechanisms of our bodies, the intricate network of neurons firing, the chemical signals coursing through our brains, the electrical impulses that orchestrate our every movement and thought. We can map brain activity with astonishing precision, identifying regions associated with specific functions: vision, memory, emotion, language. We can even intervene in these processes, altering brain chemistry with medications or stimulating specific areas to influence behavior. Yet, despite this deep understanding of the brain's machinery, the leap from mere biological processes to the subjective feeling of being alive, of experiencing the redness of a rose, the warmth of the sun, or the pang of sadness, remains a chasm. This is known as the hard problem of consciousness, coined by philosopher David Chalmers. It's the question of asterisk, why asterisk, and how physical processes in the brain give rise to subjective, qualitative experiences, or qualia. Why does a certain pattern of neural activity feel like asterisk something? Why isn't it just a complex computation happening in the dark, devoid of any inner awareness? This problem is so fundamental that it challenges our very understanding of reality. Is consciousness an emergent property of complex biological systems, arising spontaneously when a certain threshold of organization is reached? Or is it something more fundamental, a basic property of the universe itself, perhaps even present in simpler forms in non-biological systems? Theories abound. Some propose that consciousness is tied to information processing, suggesting that any system capable of complex, integrated information processing might possess some form of consciousness. Others look to quantum mechanics, speculating that quantum phenomena occurring within the microtubules of neurons might play a role, though these ideas are highly debated and often lack robust empirical evidence. Still others argue that consciousness is an illusion, a byproduct of our brain's narrative-generating mechanisms, and that the subjective experience we perceive is not a direct reflection of an underlying conscious entity. The implications of these questions are staggering. If consciousness is merely an emergent property, then understanding its origins could lead to the creation of artificial consciousness, blurring the lines between biological and artificial life. If, however, consciousness is more fundamental, it suggests a universe far richer and more interconnected than we currently comprehend, where the very fabric of reality might be imbued with a form of awareness. The subjective nature of consciousness makes it incredibly difficult to study objectively. We cannot directly access another person's qualia. We can only infer it from their behavior and reports. This inherent subjectivity creates a significant barrier to scientific investigation. We are, in essence, trying to study the very tool with which we are trying to study. The exploration of consciousness pushes the boundaries of neuroscience, philosophy, psychology, and even physics, demanding interdisciplinary collaboration and a willingness to question our most deeply held assumptions about ourselves and the universe. It is a frontier where the most profound questions about existence, identity, and the nature of reality converge, reminding us that even as we probe the furthest reaches of space, the most extraordinary universe may lie within. Within the quiet hum of our own being, the most profound of all cosmic questions patiently waits to be understood. The true meaning of quantum mechanics still puzzles us. At the heart of our understanding of the universe lies a realm so bizarre, so counterintuitive, that even its pioneers often expressed profound bewilderment. This is the realm of quantum mechanics, the physics that governs the incredibly small, the atoms, the subatomic particles, the very building blocks of existence. We have built technologies, from lasers to transistors, that rely on its principles, yet the fundamental meaning, The asterisk why and the how asterisk of its strangest phenomena remains a subject of deep philosophical and scientific debate. Imagine a world where a particle can be in multiple places at once, where observing something fundamentally changes its nature, where the universe seems to operate on probabilities rather than certainties. This is the quantum world. One of its most perplexing aspects is superposition, the idea that a quantum system can exist in a combination of all its possible states simultaneously. Think of an electron, for instance. Until it's measured, it doesn't have a definite position or momentum. It's as if it's smeared out across space, existing as a wave of probability. It's only when we interact with it, when we try to observe its position, that it collapses into a single, definite state. This collapse of the wave function is one of the central mysteries. What causes it? Is it a conscious observer, or simply any interaction with the macroscopic world? The Copenhagen interpretation, one of the earliest and most influential explanations, suggests that the act of measurement forces the quantum system to choose one of its possible outcomes. But this raises more questions than it answers. What constitutes a measurement? Does a photon hitting an electron count? Does a rock falling on a quantum particle count? And if the universe is deterministic at its fundamental level, as classical physics suggested, how can this probabilistic collapse be explained? Then there's quantum entanglement, a phenomenon so strange Einstein famously called it spooky action at a distance. When two or more particles become entangled, their fates become linked, no matter how far apart they are. If you measure a property of one entangled particle, you instantly know the corresponding property of the other, even if it's on the other side of the galaxy. This suggests a connection that transcends space and time, a hidden order that we don't fully comprehend. Does this mean information can travel faster than light? Most physicists say no, but the implications are still mind-boggling. It suggests that the universe is far more interconnected than our everyday experience would lead us to believe. We also grapple with the measurement problem. How does the continuous, deterministic evolution of the quantum wave function transition to the discrete, probabilistic outcomes we observe? Various interpretations attempt to bridge this gap, each with its own set of assumptions and challenges. The many worlds interpretation, for example, proposes that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. In one universe, the electron is here. In another, it's there. This avoids the collapse of the wave function, but introduces an unfathomable number of universes. Other interpretations, like the de Broglie-Bohm pilot wave theory, suggest that particles always have definite positions, but are guided by a pilot wave that influences their motion. This is a deterministic interpretation, but introduces non-local influences, which are also challenging to reconcile with our understanding of causality. The very act of trying to pin down the true meaning of quantum mechanics forces us to confront the limits of our own intuition, which is largely shaped by the macroscopic world. We think in terms of cause and effect, of objects having definite properties, of things being either here or there. Quantum mechanics tells us that, at its deepest level, reality operates by entirely different rules. It's a testament to the vastness of what we don't yet grasp, a humbling reminder that our current understanding is but a glimpse into a much grander, more mysterious cosmos. The quest to understand quantum mechanics is not just about particles and waves. It's about understanding the fundamental nature of reality itself, and the profound implications it has for our perception of the universe and our place within it. It is a journey into the very fabric of existence, where the familiar dissolves and the extraordinary becomes the norm, leaving us with a sense of awe and a deep appreciation for the enduring mysteries that lie just beyond our current sight. The quantum world, in its elegant yet confounding dance, whispers that the universe's deepest truths are often found not in certainty, but in the profound, peaceful embrace of the unknown. Are we alone in this vast cosmic ocean? The question of whether humanity is unique, or if life exists beyond our small blue planet, is one of the most profound and enduring mysteries we face. For centuries, philosophers, scientists, and dreamers have gazed at the stars, pondering the possibility of other worlds teeming with life, or perhaps even other intelligent civilizations. This quest is not merely an intellectual curiosity. It speaks to our deepest desires for connection, understanding, and our place within the grand tapestry of existence. The sheer scale of the cosmos is almost incomprehensible. Our Milky Way galaxy alone contains hundreds of billions of stars, and the observable universe is estimated to contain trillions of galaxies, each with billions or even trillions of stars. Within this unimaginably vast expanse, the statistical probability that Earth is the only planet capable of harboring life, let alone supporting it, seems remarkably low. Yet, despite this overwhelming statistical likelihood, we have yet to find definitive evidence of extraterrestrial life. This absence of evidence, however, is not evidence of absence. The scientific endeavor to answer this question is multifaceted, involving several key areas of research. One of the most significant is the study of exoplanets, planets orbiting stars other than our Sun. Thanks to advancements in telescope technology, such as the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite (TESS), we have discovered thousands of exoplanets, with many more candidates awaiting confirmation. These discoveries have revealed that planets are not uncommon. In fact, they appear to be a ubiquitous feature of stellar systems. More importantly, we found that many of these exoplanets reside within the habitable zone of their stars, the region where temperatures could allow for liquid water to exist on the planet's surface. Liquid water is considered a fundamental requirement for life as we know it, making these exoplanets prime candidates for further investigation. Beyond simply detecting planets, scientists are also developing methods to analyze their atmospheres. Using techniques like transmission spectroscopy, where we observe how starlight filters through an exoplanet's atmosphere as it passes in front of its star, we can look for biosignatures, chemical compounds that on Earth are strongly indicative of biological processes. Gases like oxygen, methane, and ozone, when found in certain combinations and abundances, could potentially signal the presence of life. The James Webb Space Telescope, with its unprecedented sensitivity, is poised to make significant contributions to this area of research, allowing us to probe the atmospheres of exoplanets with greater detail than ever before. Another crucial aspect of the search for extraterrestrial life is the study of extremophiles on Earth. These are organisms that thrive in environments previously thought to be inhospitable to life, such as deep-sea hydrothermal vents, highly acidic hot springs, or even within solid rock. The existence of extremophiles demonstrates that life is incredibly resilient and adaptable, expanding the range of conditions under which we might expect to find it on other worlds. If life can exist in such harsh conditions on Earth, it's plausible that similar, or even more robust, forms of life could arise and persist on planets with vastly different environments. The SETI Search for Extraterrestrial Intelligence program represents a different, yet equally vital approach. SETI projects use radio telescopes and optical telescopes to listen for deliberate signals or technological artifacts that might be produced by advanced civilizations. While the universe is vast and the chances of detecting a signal are slim, the potential reward, definitive proof of intelligent life beyond Earth, is immense. The Fermi paradox, named after physicist Enrico Fermi, highlights the apparent contradiction between the high probability of extraterrestrial civilizations existing and the lack of evidence for or contact with them. If advanced civilizations are common, why haven't we detected them? Possible explanations range from the idea that life is indeed rare, to the possibility that intelligent civilizations are short-lived, destroy themselves, or choose not to communicate. The Great Filter hypothesis suggests that there might be a barrier or series of barriers that prevent life from reaching an advanced, spacefaring stage. This filter could be in our past, meaning life is exceedingly rare to begin with, or in our future, meaning advanced civilizations inevitably face a catastrophic event. The search for extraterrestrial life also extends to our own solar system. Missions to Mars have been actively looking for evidence of past or present microbial life, given that Mars once had liquid water on its surface. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, are also considered prime candidates due to the strong evidence suggesting they harbor vast subsurface oceans of liquid water beneath their icy shells. These oceans, warmed by tidal forces, could potentially provide the necessary conditions for life to emerge and evolve, independent of sunlight. The philosophical implications of discovering extraterrestrial life are staggering. It would fundamentally alter our understanding of our place in the universe, challenging anthropocentric views and potentially inspiring new avenues of scientific inquiry and artistic expression. It could also lead to profound ethical considerations regarding our interactions with any discovered life forms, particularly if they are intelligent. Ultimately, the question of whether we are alone is a testament to the enduring human spirit of exploration and our innate drive to understand the unknown. It is a journey that pushes the boundaries of our scientific knowledge and our imagination, reminding us of the immense, awe-inspiring mystery that surrounds us. In the silent expanse, where stardust whispers and galaxies unfurl, the echo of our own existence finds its deepest resonance in the profound question of whether other voices might reply, reminding us that even in solitude, the universe is a symphony of possibility. The origin of life on Earth is a deeply buried secret. Imagine, if you will, a planet young and volatile, teeming with an energy that is both fierce and foundational. This is Earth, billions of years ago, a place utterly alien to our modern sensibilities, yet the very crucible from which all that we know, all that we are, would eventually arise. The question of how this transition occurred from inert matter to the vibrant tapestry of life remains one of science's most profound and persistent enigmas. It's not a simple question with a single neat answer. Rather, it's a vast, intricate puzzle pieced together from fragments of evidence found in ancient rocks, in the chemistry of distant stars, and in the very building blocks of our own cells. We look back across an immense chasm of time, trying to reconstruct a process that, by its very nature, left behind only the faintest of echoes. The early Earth was a very different place. The atmosphere, for instance, was likely rich in gases like methane, ammonia, water vapor, and carbon dioxide, with very little free oxygen. Volcanic activity was rampant, spewing out heat and chemicals, and the planet was frequently bombarded by asteroids and comets. Energy sources were abundant, from lightning storms of unimaginable intensity to ultraviolet radiation from the young sun, unfiltered by an ozone layer. It was within this chaotic, energetic environment that the first sparks of life might have ignited. The prevailing scientific hypothesis, known as abiogenesis, suggests that life arose from non-living matter through a series of gradual chemical reactions. It's thought that simple inorganic molecules present on early Earth could have, under these extreme conditions, self-assembled into more complex organic molecules, the precursors to life. Think of amino acids, the building blocks of proteins or nucleotides, the building blocks of DNA and RNA. Experiments, most famously the Miller-Urey experiment in the 1950s, have demonstrated that under simulated early Earth conditions, these fundamental organic molecules can indeed form spontaneously. But this is just the first, albeit crucial, step. From these simple molecules, the next challenge was to form more complex polymers, like proteins and nucleic acids. And then, the even greater leap, the spontaneous assembly of these polymers into self-replicating structures, enclosed within a boundary that could separate the internal chemistry from the external environment, the very essence of a cell. This transition from complex chemistry to self-replication is where our understanding becomes most speculative, and where the deeply buried secret truly resides. Several theories attempt to bridge this gap. One prominent idea is the RNA world hypothesis. RNA, or ribonucleic acid, is a molecule similar to DNA, but it can perform a wider range of functions, including acting as a carrier of genetic information, and crucially, as an enzyme to catalyze chemical reactions. The hypothesis suggests that in the early stages of life, RNA might have served both roles, before DNA took over as the primary genetic material and proteins became the main catalysts. Another avenue of research focuses on hydrothermal vents on the ocean floor. These vents spew out mineral-rich, chemically active fluids, providing a consistent energy source and a unique chemical environment where complex organic molecules could potentially form and organize. These vents could have acted as natural laboratories, concentrating the necessary ingredients and facilitating the chemical reactions that led to the earliest forms of life. The sheer improbability of such a complex sequence of events occurring randomly is a significant hurdle. It's not just about forming the right molecules. It's about them coming together in the right place, at the right time, and in the right sequence to achieve self-replication and evolution. This is why the origin of life remains such a captivating mystery. We are searching for the precise pathway, the specific conditions, and the fundamental principles that allowed inert matter to awaken to the stirrings of life. It's a testament to the ingenuity of nature, a process so subtle and so ancient that its complete unraveling may forever remain just beyond our direct observation, a whisper from a forgotten epoch. The evidence we find in fossilized microorganisms, in isotopic signatures in ancient rocks, and in the shared molecular machinery of all living things, are like scattered pages from a lost book, each offering a tantalizing clue, but the full narrative is still waiting to be deciphered. And so, from the silent, seething crucible of an ancient earth, a secret began to unfold, a story written not in words, but in the very fabric of existence, a gentle reminder that even the most profound beginnings can arise from the quietest of origins. The fate of our universe hangs in a delicate balance. Our universe, in its magnificent grandeur, is not a static entity. It is a dynamic, evolving system, its ultimate destiny a subject of profound scientific inquiry. For eons, the cosmic dance of expansion has captivated our minds, and understanding its future trajectory is one of the most significant challenges in modern cosmology. Imagine the universe as a grand cosmic experiment, its outcome delicately poised between several competing forces and fundamental properties. At the heart of this question lies the concept of its expansion rate, a rate that dictates whether our universe will continue to stretch indefinitely, eventually succumb to its own gravity, or perhaps even enter a cyclical phase of birth and rebirth. The expansion of the universe, as observed by Edwin Hubble in the early 20th century, is not a uniform outward movement from a single point. Rather, it is the fabric of spacetime itself that is stretching, carrying galaxies along with it. This expansion is driven by an initial impulse from the Big Bang, but it is also influenced by the total mass and energy contained within the universe. This is where the concept of cosmic density becomes crucial. If the universe's average density is above a certain critical value, its gravity would eventually halt the expansion and cause it to collapse back upon itself in a catastrophic event known as the Big Crunch. Conversely, if the density is below this critical value, the expansion would continue forever, leading to a cold, dispersed, and ultimately empty universe, a scenario sometimes referred to as the Big Freeze or heat death. However, our understanding has been dramatically reshaped by the discovery of dark energy. This enigmatic force, which seems to permeate all of space, acts as a cosmic accelerator, pushing galaxies apart at an ever-increasing rate. The presence and strength of dark energy introduce a third, and perhaps dominant, possibility for the universe's fate. If dark energy continues to dominate, the expansion will not only persist but accelerate, leading to a scenario where galaxies are ripped apart, and eventually, even atoms themselves could be torn asunder in a big rip. This is a truly mind-bending prospect, suggesting that the very structures we perceive as stable could be transient phenomena destined to dissolve. The balance is indeed delicate. The precise amount of matter and energy, the nature of dark energy, and the fundamental laws of physics all play a role in determining which of these cosmic finales will ultimately unfold. Scientists are meticulously measuring the expansion rate, the distribution of galaxies, and the properties of dark energy through sophisticated telescopes and experiments. Each new piece of data refines our models and brings us closer to an answer, yet the ultimate fate remains a tantalizing mystery, a testament to the vastness and complexity of the cosmos. The ongoing quest to understand this cosmic balance is not just an intellectual pursuit. It is a fundamental aspect of our desire to comprehend our place within this grand, unfolding narrative. And in this cosmic balance, our fleeting existence finds its quiet place, a momentary spark against an unknowable backdrop. Black holes, cosmic monsters or gateways to the unknown. Black holes. The very name conjures images of cosmic dread, of an abyss from which nothing, not even light, can escape. For decades, these enigmatic objects have been at the forefront of scientific inquiry, pushing the boundaries of our understanding of physics and the very fabric of space-time. But what are they truly? Are they merely the universe's most voracious devourers, or could they hold clues to deeper, more profound cosmic secrets? To begin our exploration, let us consider the fundamental definition. A black hole is a region of space-time where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. The boundary of the region from which no escape is possible is called the event horizon. While the event horizon acts as a one-way membrane, a point of no return, the nature of what lies beyond it remains one of science's most tantalizing mysteries. The formation of stellar black holes, the most common type, is a dramatic event. When a massive star exhausts its nuclear fuel, it can no longer support itself against the inward pull of its own gravity. The core collapses catastrophically, triggering a supernova explosion that blasts the outer layers of the star into space. What remains of the core, if it is massive enough, collapses further, compressing its matter into an infinitesimally small point known as a singularity. This singularity is the heart of the black hole, a point of infinite density and zero volume, where the known laws of physics break down. Surrounding this singularity is the event horizon, a spherical boundary whose radius, known as the Schwarzschild radius, is proportional to the black hole's mass. Crossing this threshold means an irreversible descent into the unknown. The sheer gravitational pull of a black hole is what makes it so formidable. Imagine an object with the mass of our sun compressed into a sphere only a few kilometers across. The gravitational field at its surface would be immense, warping space-time to an extreme degree. For an object falling into a black hole, the tidal forces would be immense. These forces, arising from the difference in gravitational pull on different parts of the object, would stretch it out like spaghetti, a phenomenon grimly known as spaghettification. This fate awaits any unfortunate matter that ventures too close to the event horizon. However, the concept of a black hole as merely a cosmic vacuum cleaner is a simplification. While they do accrete matter from their surroundings, they also play a crucial role in galactic evolution. Supermassive black holes, found at the centers of most galaxies, including our own Milky Way, are millions or even billions of times the mass of the Sun. These behemoths are not simply passive consumers. They can launch powerful jets of plasma that extend for thousands of light years, influencing star formation and the overall dynamics of their host galaxies. These jets, often observed in active galactic nuclei, are a testament to the immense energies involved in the processes around supermassive black holes. The study of black holes has also led to profound theoretical insights. The information paradox, for instance, is a deep puzzle that arises from the apparent conflict between quantum mechanics and general relativity. Quantum mechanics suggests that information can never be truly lost, while general relativity implies that anything falling into a black hole is irrevocably gone, its information lost forever. Stephen Hawking's groundbreaking work on Hawking radiation, a theoretical emission of particles from black holes, suggests that black holes do, in fact, evaporate over extremely long timescales. But the precise mechanism by which information is preserved or lost remains a subject of intense debate. Furthermore, the idea of black holes as gateways to the unknown is not entirely without scientific basis, albeit speculative. Some theories propose that black holes could act as conduits to other universes or even to different points in space-time. The concept of wormholes, hypothetical tunnels through space-time, is often linked to the physics of black holes. While currently residing in the realm of theoretical physics and science fiction, these ideas highlight the profound potential of black holes to challenge our most fundamental assumptions about reality. The singularity at the center of a black hole, where space-time curvature becomes infinite, could potentially be a point where our current understanding of physics ceases to apply, opening the door to entirely new realms of possibility. The scientific quest to understand black holes is ongoing. Observational astronomy, with instruments like the Event Horizon Telescope, has provided us with the first direct images of black hole event horizons, offering unprecedented glimpses into these extreme environments. These observations have largely confirmed the predictions of general relativity, but they also continue to reveal subtle anomalies and unexpected phenomena that demand further investigation. The ongoing research into black holes, from stellar remnants to galactic giants, continues to push the frontiers of our knowledge, reminding us that the universe holds secrets far grander and more mysterious than we can currently comprehend. And so, we are left with these cosmic enigmas, these points of ultimate gravitational power, blurring the lines between the known and the utterly mysterious. They are the universe's deepest whispers, reminding us that even in the face of overwhelming darkness, there is a profound and beautiful unknown that invites our quietest contemplation. The hunt for extraterrestrial intelligence continues. For millennia, humanity has gazed at the stars and pondered a fundamental question: are we alone? This profound inquiry, The search for extraterrestrial intelligence, or SETI, is one of science's most enduring and captivating pursuits. It's a quest driven by a deep-seated curiosity about our place in the cosmos and the possibility that life, in forms we can only imagine, might exist beyond our terrestrial cradle. The sheer scale of the universe is almost incomprehensible. Our Milky Way galaxy alone contains hundreds of billions of stars, and there are trillions of galaxies in the observable universe. This vastness suggests that the conditions necessary for life, as we understand it, might arise in countless other locations. Scientists have identified exoplanets, planets orbiting stars other than our Sun, with increasing frequency. Many of these exoplanets reside within what is known as the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface, a key ingredient for life as we know it. The search for extraterrestrial intelligence is not a monolithic endeavor. It encompasses various approaches. One of the most prominent is the radio astronomy component of SETI, which listens for artificial radio signals emanating from distant star systems. The logic here is that an advanced civilization like our own might use radio waves for communication or other purposes, and these signals, traveling at the speed of light, could eventually reach us. Projects like the Allen Telescope Array are dedicated to meticulously scanning the skies for such anomalous transmissions. These signals, if detected, would need to be carefully analyzed to distinguish them from natural cosmic phenomena. Beyond radio waves, scientists also consider the possibility of optical signals, such as powerful laser pulses, that an alien civilization might use for interstellar communication. The search also extends to looking for technosignatures, any evidence of technology that could be indicative of intelligent life. This could include things like unusual atmospheric compositions on exoplanets, suggesting industrial processes, or even megastructures built by advanced civilizations, like Dyson spheres designed to capture stellar energy. The challenges in this hunt are immense. The distances involved are vast, meaning any signals we detect would have originated a long time ago. Furthermore, we are limited by our current understanding of physics and biology, and the possibility exists that alien life and intelligence could be so fundamentally different from our own that we might not even recognize it if we encountered it. The philosophical implications of discovering extraterrestrial intelligence are profound. It would undoubtedly reshape our understanding of life, consciousness, and our own significance in the grand cosmic tapestry. It would be an aha moment of unparalleled magnitude, a confirmation that the universe is not merely a stage for our solitary drama, but a vibrant and perhaps populated expanse. The search continues, a testament to humanity's unyielding curiosity and its enduring hope that we are not alone in this magnificent, mysterious universe. The silent hum of the cosmos whispers the possibility of other minds, a gentle reminder that our solitude may be an illusion, woven into the vastness of the starlit dark. The enigma of dark matter persists. For decades, scientists have been grappling with a profound cosmic riddle, the undeniable existence of something that we cannot see, touch, or directly detect, yet which exerts a powerful gravitational influence on everything we can observe. This invisible substance, this cosmic phantom, has been dubbed dark matter. It's not dark in the sense of being black, like a shadow. Rather, it's dark because it doesn't interact with light. It doesn't absorb it, reflect it, or emit it, rendering it utterly invisible to our telescopes, no matter how powerful. The evidence for its presence is overwhelming, pieced together from a multitude of astronomical observations that would otherwise be inexplicable. One of the earliest and most compelling pieces of evidence comes from the rotation of galaxies. When astronomers observed spiral galaxies, they notice something peculiar. According to the visible matter alone, the stars, gas, and dust we can detect, the outer regions of these galaxies should be rotating much slower than the inner regions. Just like planets further from the Sun orbit more slowly, stars further from the galactic center should do the same. However, observations consistently show that stars in the outer reaches of galaxies are moving just as fast, if not faster, than those closer to the center. This suggests that there must be a significant amount of unseen mass, extending far beyond the visible disk of the galaxy, providing the extra gravitational pull needed to keep these fast-moving stars bound to the galaxy. This unseen mass, this dark matter halo, is estimated to be many times more massive than all the visible matter combined. Further evidence for dark matter comes from galaxy clusters, which are the largest known gravitationally bound structures in the universe. These clusters contain hundreds or even thousands of galaxies, all moving at high speeds within the cluster. If the total mass of the cluster were composed only of the visible galaxies and hot gas, the cluster would quickly fly apart. The galaxies would escape the gravitational pull of the cluster. However, these clusters remain stable, indicating the presence of a vast amount of unseen matter providing the necessary gravitational glue. The speeds of these galaxies within clusters, the gravitational lensing effects they produce, where the gravity of the cluster bends and distorts the light from more distant galaxies, all point to a mass far exceeding what we can account for with ordinary matter. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, also provides crucial evidence. The patterns of temperature fluctuations in the CMB, meticulously mapped by missions like WMAP and Planck, are incredibly sensitive to the composition of the early universe. These patterns can only be explained if dark matter was present in the early universe, playing a significant role in the formation of structures. Without dark matter, the gravitational seeds from which galaxies and galaxy clusters eventually grew would not have had enough strength to overcome the expansion of the universe and collapse into the structures we observe today. Dark matter's gravitational influence allowed ordinary matter to clump together, forming the scaffolding upon which the cosmic web we see today was built. Despite these robust lines of evidence, the exact nature of dark matter remains one of science's most profound unsolved mysteries. What is it made of? The leading candidates fall into a few broad categories. One possibility is that dark matter is composed of weakly interacting massive particles, or WIMPs. These are hypothetical particles that are much heavier than protons and neutrons and interact only through gravity and the weak nuclear force, explaining why they are so hard to detect. Experiments deep underground, shielded from other cosmic radiation, are actively searching for these elusive WIMPs, attempting to catch a rare interaction with ordinary matter. So far, no definitive detection has been made. Another class of candidates includes axions, very light, hypothetical particles that were originally proposed to solve a problem in particle physics. These are much lighter than WIMPs and would interact even more weakly, making their detection even more challenging. Other theories propose modifications to gravity itself, suggesting that perhaps our understanding of gravity on cosmic scales is incomplete, and that the observed phenomena are not due to extra matter, but to a different gravitational law. However, these theories face significant challenges in explaining all the observed data consistently. The search for dark matter is a testament to the scientific method's relentless pursuit of understanding. It highlights the limitations of our current knowledge and the vastness of the universe's hidden architecture. We see its effects, we map its gravitational influence, but its fundamental identity remains shrouded in cosmic silence. This persistent enigma drives innovation in experimental physics and theoretical cosmology, pushing the boundaries of our comprehension and reminding us that much of the universe's story is yet to be told, waiting in the unseen. And in the quiet expanse, the unseen hand of dark matter shapes the cosmic dance, a constant reminder that the universe holds secrets far vaster than our current sight can comprehend. The mystery of dark energy continues to expand our ignorance. Imagine, if you will, a vast, silent ocean, stretching further than the mind can comfortably comprehend. We, as observers, stand on the shore, charting the currents, understanding the waves, and even mapping the depths we can reach with our instruments. Yet a profound realization dawns. The water we can see, the water we can touch, the water that makes up all the ships and islands and creatures we know, this is but a tiny fraction of the ocean's true expanse. This is the essence of dark energy's mystery, a force that seems to permeate the very fabric of the cosmos, driving its accelerated expansion, yet remaining stubbornly hidden from our direct observation, a profound testament to how much of reality lies beyond our current ken. For decades, astronomers believed the universe's expansion, initiated by the Big Bang, was slowing down, its momentum gradually being reined in by the gravitational pull of all the matter within it. This was a comforting, if vast, picture, a universe with a definite amount of stuff, a cosmic budget that would eventually determine its ultimate destiny, perhaps a slow, cold contraction back into a singularity, or a gradual fade into an eternal stillness. But in the late 1990s, observations of distant supernovae, those brilliant stellar explosions that act as cosmic lighthouses, began to paint a radically different and deeply unsettling portrait. These supernovae, used as standard candles to measure cosmic distances, appeared fainter than expected, meaning they were further away than they should be if the universe's expansion were decelerating. This anomaly suggested something was actively pushing galaxies apart, not just the initial impetus of the Big Bang, but an ongoing, pervasive force. This enigmatic force was dubbed dark energy. It's not matter as we understand it, nor is it dark matter, which we know interacts gravitationally. Dark energy seems to be an intrinsic property of space itself. As space expands, more space is created, and with it, more dark energy, leading to an ever-increasing rate of expansion. It's like an invisible hand, gently but persistently nudging everything apart, overcoming the very gravity that should be holding it together. The implications are staggering. If dark energy continues to dominate, the universe's future is one of increasing isolation. Galaxies will recede from each other at ever-accelerating speeds. Eventually, they will become so distant that their light will no longer be able to reach us, effectively disappearing from our observable horizon. Our own Milky Way galaxy, along with its local group of galaxies, might remain gravitationally bound, but the rest of the universe would become an unreachable, invisible void. This scenario is often referred to as the Big Freeze or the Big Rip, depending on the precise nature and evolution of dark energy. The current leading theoretical explanation for dark energy is the cosmological constant, a concept first introduced by Albert Einstein, who later famously called it his biggest blunder. This constant represents a uniform energy density inherent in empty space. However, theoretical calculations based on quantum field theory predict a value for this vacuum energy that is vastly, astronomically larger than what is observed, by a factor of 10 to the power of 120. This immense discrepancy, known as the cosmological constant problem, is one of the most significant challenges in modern physics, suggesting a fundamental misunderstanding of either gravity, quantum mechanics, or both. Other theories propose that dark energy might not be constant but could be a dynamic field, sometimes called quintessence, that changes over time and space. However, even these models struggle to explain the precise value and behavior of dark energy that we observe. The mystery deepens when we consider that dark energy, along with dark matter, constitutes approximately 95% of the total mass energy content of the universe. The ordinary matter that makes up stars, planets, and ourselves accounts for a mere 5%. We are, in essence, living on a tiny island of the known, adrift in a cosmic sea of the utterly mysterious. This profound ignorance is not a cause for despair, but an invitation to wonder. It reminds us that the universe is far grander and more complex than our current understanding allows. It highlights the limits of our perception and the vast frontiers of knowledge yet to be explored. The quest to understand dark energy is not just about unraveling a cosmic puzzle. It is about understanding our place in the universe, the fundamental laws that govern existence, and the ultimate fate of everything we know. It is a humbling reminder that even as we unlock incredible secrets, the universe holds an even greater capacity for surprise, for the unknown, for a quiet, majestic wonder that continues to expand our horizons, even as it expands the universe itself. In the silent, accelerating dark, we find a profound truth. The universe's greatest expansions are often born from our deepest unknowns. The multiverse hypothesis. Are there other realities? The idea that our universe might not be the only one, that an immense, perhaps infinite collection of universes, a multiverse, could exist alongside our own, is a concept that stretches the very limits of our imagination and our current scientific understanding. It's a hypothesis born from some of the most profound and perplexing observations and theories in modern physics, particularly in cosmology and quantum mechanics. Imagine, if you will, that every decision made, every quantum fluctuation, every possible outcome of an event might not just be a theoretical possibility, but a realized reality in another universe. This is the tantalizing, and for some, unsettling, prospect that the multiverse hypothesis presents. One of the primary drivers for the multiverse hypothesis comes from the inflationary theory of cosmology. This theory posits that in the earliest moments after the Big Bang, the universe underwent an incredibly rapid period of expansion. While this theory successfully explains many observed features of our universe, such as its flatness and uniformity, some models of inflation suggest that this process might not have stopped everywhere simultaneously. Instead, inflation could be eternal, continuing in some regions of space while other regions, like our own observable universe, have bubbled off and ceased inflating. In this scenario, each of these bubble universes could be distinct, with their own unique physical constants, laws, and even dimensions. They would be causally disconnected from our own, meaning we could never observe or interact with them, making them entirely separate realities. Another avenue leading to the multiverse concept arises from interpretations of quantum mechanics, particularly the many worlds interpretation, MWI. Quantum mechanics, the theory governing the very small, is famously probabilistic. A particle, for instance, can exist in a superposition of multiple states simultaneously until it is observed, at which point it collapses into a single state. The MWI proposed by Hugh Everett III offers a radical solution to this measurement problem. Instead of collapsing, it suggests that every time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different possible outcome. In one universe, the particle is here. In another, it's there. In one, you chose coffee. In another, you chose tea. This interpretation suggests an ever-branching tree of realities, each a consequence of a quantum event. While conceptually elegant in avoiding the problematic collapse postulate, the MWI implies an unfathomably vast and ever-increasing number of universes. Furthermore, string theory, a leading candidate for a theory of everything, which attempts to unify all fundamental forces and particles, also hints at a multiverse. String theory requires the existence of extra-spatial dimensions beyond the three we perceive. The way these extra dimensions are compactified or curled up can lead to an enormous number of possible configurations, each potentially giving rise to a universe with different fundamental physical constants and laws. This vast landscape of possibilities within string theory suggests that our universe, with its specific set of laws, might just be one of many vacua or stable states within this larger string landscape. The anthropic principle also plays a role in the discussion. This principle, in its various forms, suggests that the observed values of physical constants in our universe are precisely what they are because if they were even slightly different, life as we know it, or indeed any complex structure, could not exist. For example, the strength of gravity, the mass of fundamental particles, and the cosmological constant all appear to be finely tuned for the existence of stars, galaxies, and ultimately ourselves. If our universe is just one of an immense number of universes, each with randomly varying constants, then it's not surprising that we find ourselves in one where the conditions are just right for our existence. It's a form of selection bias. We can only observe a universe capable of supporting observers. However, the multiverse hypothesis is not without its challenges and criticisms. A major hurdle is its testability. By definition, many proposed multiverse scenarios involve universes that are causally disconnected from our own, making direct observation and empirical verification extremely difficult, if not impossible. This raises questions about whether the multiverse is truly a scientific hypothesis, or more of a philosophical or metaphysical concept, as science relies on falsifiable predictions. Some scientists argue that while the mathematical frameworks might allow for multiverses, without a way to test these ideas, they remain speculative. Despite these challenges, the pursuit of understanding the multiverse continues. It offers potential explanations for some of the deepest mysteries we face, such as the origin of our universe, the seemingly fine-tuned nature of its laws, and the puzzling nature of quantum phenomena. It forces us to confront our place in the cosmos, suggesting that what we perceive as the entirety of existence might just be a tiny, perhaps even insignificant, speck within a grander, more complex tapestry of realities. The exploration of these hypothetical realms, even if only through theoretical physics and philosophical contemplation, expands our perspective and underscores the profound depth of the unknown. And so, the possibility of other realities, stretching beyond our comprehension, reminds us that the vastness of existence may extend far beyond the stars we can see, into realms we can only begin to imagine. The nature of gravity is more complex than we imagine. When we think of gravity, we often picture a simple force, a gentle pull holding us to the Earth, keeping the moon in orbit around our planet, and the planets tethered to the sun. It's a fundamental aspect of our everyday experience, so pervasive that we rarely question its underlying nature. Yet, as we delve deeper into the universe and the intricate workings of physics, we discover that gravity is far more profound, more enigmatic, and more complex than our initial intuitions suggest. For centuries, our understanding was dominated by Isaac Newton's law of universal gravitation, a remarkably accurate description of how objects with mass attract each other. Newton proposed that this attraction is instantaneous, acting across vast distances, and that its strength is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. This elegant mathematical framework allowed us to predict the motion of celestial bodies with astonishing precision, forming the bedrock of classical mechanics and enabling groundbreaking achievements like the mapping of the solar system and the prediction of planetary orbits. It was a triumph of human intellect, a testament to our ability to discern order in the apparent chaos of the cosmos. However, even Newton himself acknowledged limitations, particularly when considering the nature of this force and how it could possibly propagate across the vacuum of space without any visible medium. His description was phenomenological, explaining how gravity behaved, but not why asterisk or what it truly was. The true revolution in our understanding came with Albert Einstein's theory of general relativity, published in 1915. Einstein proposed a radical departure from Newton's view, suggesting that gravity is not a force in the traditional sense, but rather a manifestation of the curvature of space-time. Imagine space-time as a vast, invisible fabric that permeates the entire universe. Massive objects like stars and planets warp and bend this fabric around them, much like a heavy ball placed on a stretched rubber sheet creates a dip. What we perceive as the force of gravity is, in fact, the motion of objects following the curves in this space-time. A smaller object, like a marble rolling on that same rubber sheet, will naturally be drawn towards the dip created by the heavier ball, not because of a direct pull, but because it is following the contours of the bent surface. This concept of gravity as a geometric property of space-time is profoundly counterintuitive. It suggests that space and time are not static, unchanging backdrops against which events unfold, but are dynamic entities, intimately interwoven and influenced by the presence of matter and energy. General relativity has been extraordinarily successful in explaining phenomena that Newtonian gravity could not. For instance, it accurately predicts the slight deviation in Mercury's orbit around the Sun, a discrepancy that had puzzled astronomers for decades. It also predicts the bending of light by massive objects, a phenomenon that was famously confirmed during a solar eclipse in 1919, catapulting Einstein to global fame. Black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape, are a direct consequence of general relativity. The extreme warping of space-time near these objects creates a point of no return, a boundary known as the event horizon. Furthermore, general relativity predicts the existence of gravitational waves, ripples in the fabric of space-time caused by cataclysmic cosmic events, such as the collision of black holes or neutron stars. These waves, once purely theoretical, were directly detected for the first time in 2015 by the LIGO experiment, marking another monumental triumph for Einstein's theory and opening a new window for observing the universe. However, despite its immense success, general relativity is not the final word. One of the most significant challenges lies in reconciling it with quantum mechanics, the theory that describes the universe at the smallest scales. Gravity, as described by Einstein, is a continuous, smooth phenomenon, while quantum mechanics deals with discrete packets of energy and probabilistic interactions. Attempts to quantize gravity, to create a theory of quantum gravity, have proven incredibly difficult. Physicists are exploring various avenues, such as string theory and loop quantum gravity, in the hope of unifying these two pillars of modern physics. These theories suggest that gravity might be mediated by a fundamental particle, the graviton, analogous to how other forces are mediated by particles like photons, for electromagnetism, and gluons, for the strong nuclear force. But the graviton, if it exists, has yet to be detected, and its properties remain largely theoretical. Another complexity arises when we consider the universe on its largest scales. Observations of galaxies and galaxy clusters suggest that the visible matter we can detect, stars, gas, dust, accounts for only a small fraction of the total mass and energy in the universe. The vast majority, about 95%, is composed of mysterious substances known as dark matter and dark energy. Dark matter, as its name suggests, does not interact with light, making it invisible to our telescopes, but its gravitational influence is evident in the rotation of galaxies and the structure of cosmic webs. Dark energy, even more perplexing, appears to be responsible for the accelerating expansion of the universe, a discovery that earned the Nobel Prize in Physics in 2011. The nature of both dark matter and dark energy remains one of the biggest unsolved mysteries in science, and their existence profoundly impacts our understanding of gravity's role on a cosmic scale. Are these phenomena indicative of new physics beyond general relativity, or are they simply manifestations of gravity behaving in ways we haven't yet fully grasped? The universe, it seems, holds its deepest secrets close, and gravity, the unseen architect of cosmic structure, continues to be a profound source of wonder and investigation. The fabric of reality bends and weaves, a silent dance of mass and energy, reminding us that even the most familiar forces hold a universe of unanswered questions. The search for a unified theory of everything goes on. For centuries, humanity has gazed at the stars and pondered the fundamental workings of the cosmos. We've developed incredible frameworks to describe the universe, but they remain, in a way, separate. On one hand, we have general relativity, Einstein's masterpiece, which beautifully explains gravity and the large-scale structure of the universe, the dance of planets, the majestic sweep of galaxies. It describes the smooth, continuous fabric of spacetime, warping and bending under the influence of mass and energy. It's a theory of the grand, the colossal, the cosmic ballet. Then, on the other hand, we have quantum mechanics, a realm of the incredibly small, the subatomic. This theory governs the behavior of particles, the very building blocks of matter and energy. It's a world of probabilities, of discrete packets of energy called quanta, of particles that can be in multiple places at once, and of forces that are mediated by exchange particles. It's a theory of the tiny, the strange, the probabilistic dance of fundamental constituents. The profound challenge, the great unsolved mystery that occupies the minds of many physicists, is that these two pillars of modern physics, these incredibly successful theories, are fundamentally incompatible. They speak different languages, employ different mathematical tools, and make predictions that, at the extreme scales where both should theoretically apply, lead to nonsensical results, infinities, or outright contradictions. Imagine trying to use a map of the entire world to navigate the intricate pathways of a single neuron. The scales and the principles are just too different. When we try to describe phenomena where both gravity and quantum effects are significant, such as the conditions at the very beginning of the universe, in the heart of a black hole, or at the Planck scale, an unimaginably tiny length of about 1.6 x 10^3 meters, our current theories break down. General relativity, with its smooth space-time, doesn't account for the quantum fluctuations that should be present at such scales. Quantum mechanics, in its current form, doesn't adequately incorporate gravity's dominant influence at these extreme densities and energies. Physicists dream of a theory of everything, a single, elegant framework that would unify all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, and describe all elementary particles within a single, coherent mathematical structure. It would be a single set of rules that governs everything, from the smallest subatomic particle to the largest supercluster of galaxies. It would explain why the fundamental constants of nature have the values they do, and perhaps even shed light on why the universe exists at all. This quest has led to various promising, yet incomplete, avenues of research. String theory, for instance, proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. Different vibration modes of these strings correspond to different particles and forces, including gravity. It's a mathematically rich framework that naturally incorporates gravity and has the potential to unify all known forces. However, string theory operates in more than the 4 dimensions we perceive, 3 spatial and 1 temporal, often requiring 10 or 11 dimensions, and its predictions are incredibly difficult to test experimentally due to the immense energies required to probe the string scale. Another contender is loop quantum gravity, which attempts to quantize spacetime itself, suggesting that spacetime is not continuous but granular, made up of discrete loops, or atoms of spacetime. This approach directly tackles the quantum nature of gravity without invoking extra dimensions or fundamental strings. While it offers a compelling picture of quantum spacetime, it faces challenges in recovering the smooth spacetime of general relativity at larger scales and fully incorporating the other fundamental forces. Other approaches explore different mathematical landscapes, seeking connections between quantum mechanics and gravity through concepts like emergent gravity, where gravity itself arises from more fundamental quantum phenomena, or through modifications to our understanding of spacetime at very small scales. The search is a testament to the human intellect's relentless pursuit of understanding, a philosophical endeavor to find order and simplicity within the apparent complexity of existence. It is a journey fueled by profound curiosity, a desire to peel back the layers of reality and glimpse the underlying unified truth. While a definitive theory of everything remains elusive, the ongoing search pushes the boundaries of our knowledge, leading to new insights and unexpected discoveries in mathematics, particle physics, and cosmology. Each failed attempt, each new hypothesis, refines our understanding and brings us, perhaps incrementally, closer to that ultimate unifying vision. The universe whispers its secrets in many tongues, but the dream of a single, harmonious language to understand them all continues to resonate through the quiet hum of existence. The paradoxes of quantum entanglement defy intuition. Imagine, if you will, 2 tiny particles, perhaps electrons born from the same event, forever linked. This is the essence of quantum entanglement, a phenomenon so peculiar it famously troubled even Albert Einstein, who described it as spooky action at a distance. In classical physics, if you have 2 separate objects, what happens to one has no immediate effect on the other, unless a force travels between them. But in the quantum realm, entanglement breaks this fundamental rule of locality. When 2 particles become entangled, their fates are intertwined in a way that transcends the usual limitations of space and time. Let's delve a little deeper into this bewildering concept. When particles are entangled, they share a common quantum state. This means that certain properties, like their spin or polarization, are correlated, no matter how far apart they are. If you measure the spin of one entangled particle and find it to be up, you instantly know that the spin of its entangled partner, even if it's light years away, must be down. This instantaneous correlation, this apparent violation of the speed of light, is what makes entanglement so mind-boggling. It's as if these particles are communicating with each other, not through any physical signal, but through an invisible, instantaneous bond. The paradoxes arise when we try to reconcile this with our everyday understanding of reality. Einstein, for instance, believed that this suggested quantum mechanics was incomplete, that there must be some hidden variables, some predetermined properties that we simply weren't aware of. He famously used the analogy of a pair of gloves. If you find a left-handed glove in one box, you instantly know the other box contains a right-handed glove. But this isn't spooky. It's just that the gloves were already determined to be left and right when they were separated. However, experiments, most notably those based on Bell's theorem, have consistently shown that the correlations observed in entangled particles are stronger than any theory based on hidden variables could explain. The universe, it seems, is not playing by those classical rules. This implies that the properties of these entangled particles are not predetermined. Instead, they are indeterminate until a measurement is made. The act of measuring one particle seems to instantaneously influence the state of the other, collapsing their shared, indefinite state into a definite one. This is not a message being sent. It's a shared reality being revealed. The implications are profound. It challenges our very notions of causality, locality, and the objective reality of physical properties. If the properties of a particle don't exist until measured, and measuring one instantaneously affects another, then what does it mean for a particle to have a property? Consider the concept of quantum superposition. Before measurement, an entangled particle and its partner exist in a superposition of states, both up and down simultaneously, for example. It's only when we interact with one that this fuzzy, probabilistic existence solidifies into a definite reality for both. This interconnectedness suggests that the universe might be far more unified and less fragmented than we perceive. The distance between entangled particles becomes a human construct, a limitation of our macroscopic perspective, rather than a fundamental barrier in the quantum fabric of reality. This isn't just a theoretical curiosity. Entanglement has become a cornerstone for emerging quantum technologies. Quantum computers, for instance, leverage entanglement to perform calculations that are impossible for even the most powerful classical computers. Quantum cryptography uses entanglement to create unbreakable codes, where any attempt to eavesdrop would immediately break the entanglement and alert the users. Even quantum teleportation, the transfer of quantum information from one location to another, relies on this peculiar connection. The beauty of entanglement lies in its defiance of our ingrained intuitions. We are accustomed to a world where cause and effect are sequential, where influences travel at finite speeds, and where objects have definite properties. Entanglement shatters these assumptions, offering a glimpse into a reality that is far stranger, more interconnected, and perhaps more wondrous than we can easily comprehend. It forces us to question what we mean by separate, instantaneous, and even real. The universe, at its most fundamental level, appears to be a vast, intricate web of interconnectedness, where the fate of one particle is intrinsically linked to the fate of its distant partner, a silent, profound dance across the cosmos. In this cosmic ballet, distance dissolves, and the universe whispers of a deeper unity. The fine-tuning of the universe, a cosmic coincidence. Imagine, if you will, the grand tapestry of existence, woven from countless threads of physical laws and fundamental constants. For decades, scientists have observed a peculiar characteristic of our universe. It appears to be exquisitely fine-tuned for life, or at least, for the existence of complex structures like stars, planets, and ultimately ourselves. This isn't a matter of mere coincidence. It's a profound observation that has led to a great deal of contemplation. Consider the fundamental forces like gravity, electromagnetism, and the nuclear forces. If their strengths were even minutely different, the universe as we know it would be impossible. For instance, if gravity were slightly stronger, stars would burn out far too quickly, leaving no time for planets to form or for life to evolve. If it were weaker, stars might not form at all. The mass of the proton and neutron, the charge of the electron, the cosmological constant. All these seemingly arbitrary numbers appear to be set within incredibly narrow ranges that permit the universe to exist in a stable, life-sustaining manner. The cosmological constant, for example, represents the energy density of empty space. Theoretical calculations suggest it should be an astronomically large number, vastly different from the tiny value we actually observe. If the cosmological constant were even a little bit larger, the universe would have expanded so rapidly after the Big Bang that no galaxies or stars could have ever formed. If it were significantly smaller, the universe might have collapsed back on itself before it even had a chance to evolve. This precision is so remarkable that it has led some to speculate about the possibility of a multiverse, where our universe is just one of an infinite number of universes, each with different physical constants. In such a scenario, it wouldn't be surprising that we find ourselves in one of the rare universes that happens to be hospitable to life. This is often referred to as the anthropic principle, the idea that we observe the universe to be the way it is because, if it were any different, we wouldn't be here to observe it. Another example of fine-tuning relates to the abundance of hydrogen and helium in the early universe. During the Big Bang, nuclear fusion created these elements. The precise balance of nuclear forces and particle masses determined the exact ratio of hydrogen to helium. If this ratio were different, the formation of heavier elements, essential for rocky planets and life, would have been severely hampered. Even the number of spatial dimensions, which we perceive as 3, is thought to be critical. If there were more or fewer dimensions, the fundamental laws of physics, particularly electromagnetism, would behave very differently, potentially preventing the formation of stable atoms or complex molecules. The implications of this fine-tuning are far-reaching. It challenges our understanding of causality and randomness. Is it merely a fortunate accident, a cosmic lottery win, or does it hint at a deeper, underlying structure or purpose to the universe? This question has occupied philosophers and scientists for centuries, pushing the boundaries of our knowledge and our imagination. It invites us to ponder our place in the cosmos, not as isolated observers, but as integral parts of a system that seems, in its very essence, to be predisposed to our existence. The delicate balance of the cosmos whispers a profound truth, that even in the vastness of the unknown, the improbable may be the very condition for our being. The limits of our perception shape our understanding. Our senses, the very windows through which we perceive the world, are remarkably limited, and it is within these inherent constraints that our understanding of reality is forged. Consider the vast electromagnetic spectrum. Humans, for instance, can only see a tiny sliver of it, the visible light spectrum, ranging from deep violet to fiery red. We are oblivious to the pervasive waves of radio signals, the warming embrace of infrared radiation, the invisible rays of ultraviolet light that tan our skin, the penetrating power of X-rays, and the energetic punch of gamma rays. Each of these forms of radiation carries information about the universe, about distant stars, about the very composition of matter, yet they remain largely unseen, unheard, and unfelt by our biological apparatus. Our visual world is but a curated subset of the actual energetic exchanges happening all around us. Similarly, our auditory range is confined. We can detect sound waves within a specific frequency band, typically from about 20 Hz to 20,000 Hz. Below this, infrasound, generated by geological events or large animals, exists, and above it, ultrasound, used by bats and dolphins, permeates the environment. Yet we are deaf to these sonic landscapes. The universe is alive with vibrations and resonances that fall outside our hearing, shaping the experiences of other creatures and influencing subtle environmental dynamics that we never perceive. Our sense of touch, while sophisticated, is also limited in its sensitivity to pressure, temperature, and texture. We cannot feel the subtle shifts in atmospheric pressure that precede weather changes, nor can we directly perceive the molecular forces that bind objects together. Our olfactory and gustatory senses, while crucial for survival, are relatively crude compared to those of many other species. Dogs, for example, possess olfactory capabilities millions of times more sensitive than ours, allowing them to navigate and understand their world through scent in ways that are utterly foreign to us. The chemical language of the world, the subtle pheromonal signals, the intricate molecular bouquets, are largely a closed book to our human noses. Beyond these direct sensory limitations, our cognitive frameworks also impose boundaries on our understanding. Our brains are wired to find patterns, to simplify complexity, and to create narratives that make sense of our experiences. This is an evolutionary advantage, allowing us to react quickly and efficiently in a dynamic environment. However, this drive for simplification can lead us to overlook the truly nuanced, the exquisitely complex, and the profoundly counterintuitive aspects of reality. Concepts like quantum superposition, where a particle can exist in multiple states simultaneously, or the bending of space-time by gravity, challenge our everyday intuitions, which are built upon the macroscopic classical world. The very language we use to describe reality is a product of our perception. Words are symbols, approximations of the vastness of experience. When we try to describe the ineffable, the sublime, or the deeply abstract, our language often falters, revealing the limitations of our conceptual tools. The scientific method, with its emphasis on objective measurement and empirical evidence, is a powerful attempt to transcend these subjective limitations, to build instruments and devise experiments that can extend our reach beyond our natural senses. Telescopes reveal galaxies light years away, microscopes unveil the hidden architecture of cells, and sophisticated detectors probe the subatomic realm. These tools act as prosthetic senses, expanding our perceptual horizons and allowing us to glimpse aspects of the universe that would otherwise remain forever hidden. Even with these advancements, we are still prisoners of our own biological and cognitive architecture. Our understanding of time, for instance, is deeply anthropocentric, tied to our linear experience of past, present, and future. Relativity, however, suggests that time is not absolute but is interwoven with space, forming a dynamic fabric that can be stretched and warped. Our minds struggle to truly grasp the implications of a universe where time can flow differently for different observers, or where the past, present, and future might, in some sense, coexist. The very act of observation in quantum mechanics highlights this perceptual limit. The observer effect suggests that the act of measuring a quantum system can fundamentally alter its state. This implies that our interaction with reality is not a passive reception of information, but an active participation in its unfolding. The universe, in this view, is not simply out there, waiting to be discovered in a predetermined state, but is, in part, shaped by our very act of perceiving it. This profound idea challenges our deeply ingrained notion of an objective, independent reality, suggesting instead a more interconnected and participatory cosmos. Our understanding is also shaped by the evolutionary pressures that guided our development. We evolved to survive and reproduce in a specific environment, and our perceptual and cognitive systems are optimized for that purpose. The vastness of cosmic scales, the infinitesimally small realms of quantum physics, and the abstract realms of pure mathematics often lie far outside the scope of these evolved mechanisms. It is through deliberate intellectual effort, through the pursuit of abstract thought and the development of sophisticated conceptual models, that we can begin to approach these alien domains of knowledge. The universe, in its entirety, is likely far more intricate, more bizarre, and more wondrous than our limited human perception can ever fully encompass. The limitations of our perception are not a cause for despair, but rather an invitation to humility and wonder. They remind us that our current understanding is a work in progress, a tentative map of an immeasurably vast and complex territory. Each new discovery, each expansion of our knowledge, reveals not only new truths but also new depths of the unknown, new horizons of mystery that beckon us forward. The universe is a grand tapestry woven with threads we can perceive and countless more that remain invisible to us. A silent symphony playing in frequencies we cannot hear, a cosmic dance performed in dimensions beyond our sight. Our understanding is a reflection, however imperfect, of this boundless reality, a starlight filtered through the lens of our own being. And so, we find that our understanding is not a mirror reflecting the universe perfectly, but a unique lens, shaped by our biology and our history, that allows us to glimpse its profound and often surprising nature. The true nature of reality might be fundamentally different. We often navigate our lives with a comfortable certainty about the world around us, a tangible reality built upon the solid foundation of our senses and the laws of physics as we understand them. We see the chair, we feel the ground beneath our feet, we witness the predictable arc of a thrown ball. This is the reality we inhabit, the one that dictates our daily actions and shapes our understanding of existence. Yet, as we delve deeper into the very fabric of the cosmos and the subtle whispers of quantum mechanics, this seemingly unshakable foundation begins to shimmer, hinting at possibilities that could redefine our very notion of what is real. For centuries, philosophers and scientists alike have grappled with the idea that our perception of reality might be a sophisticated illusion, a limited interpretation of a much grander and perhaps stranger underlying structure. Consider, for instance, the implications of quantum entanglement. When two particles become entangled, they are inextricably linked, regardless of the distance separating them. If you measure a property of one particle, the other instantaneously assumes a corresponding state, as if they are communicating faster than the speed of light, a feat that appears to defy our everyday understanding of space and time. This interconnectedness suggests that at the most fundamental level, the universe might not be composed of discrete, independent entities, but rather a continuous, interwoven tapestry where separation is an illusion. The very concept of individual objects, distinct and separate from their surroundings, could be a macroscopic approximation, a simplification that our brains construct to make sense of an overwhelmingly complex quantum realm. Furthermore, the nature of observation itself plays a peculiar role in quantum physics. Before an observation is made, a quantum particle can exist in a superposition of states, meaning it simultaneously occupies multiple possibilities. It is only when we observe it that it collapses into a single, definite state. This suggests that consciousness, or at least the act of measurement, might not be a passive observer of reality, but an active participant in its creation. Our very act of looking could be shaping the reality we perceive. This challenges the classical view of an objective reality that exists independently of any observer, hinting instead at a more participatory universe where the observer and the observed are deeply intertwined. The philosophical implications of these scientific discoveries are profound. If reality is not as it appears, if it is fundamentally probabilistic, interconnected, and potentially shaped by observation, then our assumptions about causality, determinism, and even our own agency might need re-evaluation. Concepts like the hard problem of consciousness, the persistent mystery of how subjective experience arises from physical matter, further underscore the potential for reality to be far more complex and nuanced than our current models allow. Perhaps what we experience as reality is merely a projection, a limited interface designed for biological survival, hiding a deeper, more abstract, and perhaps even more beautiful truth. The universe might be a grand simulation, a holographic projection, or a manifestation of pure information, with the physical world we perceive being merely an emergent property. These are not just flights of fancy. They are serious scientific hypotheses being explored, driven by the persistent anomalies and unanswered questions that arise from our deepest investigations into the cosmos. The more we learn, the more we realize how much we don't know, and how much of what we think we know might be a comforting, but ultimately incomplete, interpretation of a far more intricate and astonishing existence. The universe is not just what we see. It is a realm of possibilities so vast that our current understanding is but a single, faint ray of light in an infinite, unexplored darkness. The universe whispers truths our senses cannot grasp, and reality may be a dream we are only beginning to awaken from. The search for exotic particles continues. Beneath the familiar tapestry of protons, neutrons, and electrons, the universe harbors a hidden world of particles, some so fleeting and elusive they challenge our very ability to detect them. These are the exotic particles, entities that do not fit neatly into the standard model of particle physics, the reigning theory that describes the fundamental building blocks of matter and their interactions. For decades, scientists have been on a relentless quest, pushing the boundaries of experimental physics with ever more powerful accelerators and sensitive detectors, hoping to glimpse these theoretical whispers and unlock deeper secrets about the cosmos. One of the most sought-after exotic particles is the hypothetical ****graviton***. In the grand unification efforts of physics, the standard model successfully describes three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, through the exchange of specific particles. However, gravity, the force that shapes galaxies and holds us to the Earth, remains stubbornly outside this framework. Physicists theorize that gravity, too, must have a quantum carrier particle, a massless boson called the graviton. Detecting a graviton is an immense challenge because gravitational interactions are incredibly weak, far weaker than the other forces. Imagine trying to detect the ripple from a single pebble, dropped in an ocean stretching across the entire observable universe. The energy required to produce and detect a single graviton is astronomically high, far beyond the capabilities of our current technology. Yet, the theoretical necessity of its existence drives the ongoing search, hinting at a more complete understanding of how spacetime itself is woven. Another class of exotic particles that has captured the imagination of physicists are supersymmetric particles, often referred to as sparticles. Supersymmetry, or SUSY, is a theoretical extension of the standard model that postulates a symmetry between fundamental particles called bosons and fermions. For every known fermion, like electrons and quarks, SUSY predicts a heavier superpartner fermion, and for every known boson, like photons and Higgs bosons, it predicts a heavier superpartner boson. These predicted sparticles, such as the ***neutralino** or the ***chargino, could be candidates for ***dark matter**, the mysterious substance that accounts for roughly 27% of the universe's mass energy, but does not interact with light. Experiments at particle colliders like the Large Hadron Collider, LHC, are meticulously searching for evidence of these superpartners, meticulously analyzing collision data for any anomalies that might point to their existence. The absence of direct detection so far has led to refinements in theoretical models, but the possibility of supersymmetry remains a vibrant area of research. Beyond dark matter candidates, exotic particles also emerge from theories attempting to explain other cosmic puzzles. For instance, the existence of magnetic monopoles hypothetical particles that possess only a single magnetic pole, either north or south, but not both, has been theorized for decades. If they exist, they could help explain the uniform distribution of matter in the early universe. Similarly, the search for actions, another proposed dark matter candidate, is gaining momentum. These very light, weakly interacting particles were originally conceived to solve a problem in quantum chromodynamics, QCD, the theory of the strong nuclear force, but have since been repurposed as potential dark matter constituents. Experiments are employing highly sensitive detectors designed to catch these elusive axions by looking for their potential conversion into photons in the presence of strong magnetic fields. The pursuit of these exotic particles is not merely an academic exercise. It is a fundamental exploration of the universe's deepest constituents. Each new particle discovered, or each theoretical prediction that is experimentally disproven, refines our understanding of the cosmos and nudges us closer to a complete picture of reality. These particles, though unseen and unfelt by our everyday senses, are the silent architects of the universe, their existence or non-existence profoundly shaping the cosmos we inhabit. The search is a testament to human curiosity, a relentless drive to peel back the layers of the unknown and comprehend the fundamental forces and particles that govern existence. The unknown particles whisper of a universe far grander and more intricate than our current models can fully capture, a cosmic symphony played in frequencies we are still learning to hear. The mysteries of the human brain remain largely uncharted. Our brains, these extraordinary organs nestled within our skulls, are the very seat of our consciousness, our thoughts, our emotions, and our memories. Yet, despite millennia of philosophical contemplation and decades of dedicated scientific inquiry, the sheer complexity of the human brain means that vast swathes of its intricate workings remain shrouded in mystery. Imagine a universe contained within a mere 3 pounds of tissue, a universe teeming with billions of neurons, each one capable of forming thousands of connections, creating a network so vast and intricate that it dwarfs even the most complex supercomputers we can conceive. This is the frontier of neuroscience, a landscape where every discovery seems to unlock a cascade of new questions, pushing the boundaries of our understanding ever outward. Consider, for instance, the phenomenon of memory. We can recall vivid details from our childhood, the scent of a long-forgotten flower, the sound of a loved one's voice, yet pinpointing the exact physical location and mechanism by which these memories are stored and retrieved remains a profound challenge. While we have identified areas involved in memory formation, like the hippocampus, the precise encoding and retrieval processes, the way electrical and chemical signals coalesce into a coherent recollection, are still subjects of intense research. It's as if we have a magnificent library, but we're still deciphering the Dewey Decimal System for every single book. Then there's the enigma of consciousness itself. What is it that allows us to experience the world subjectively? What is the self that perceives and reflects? While neuroscientists can correlate brain activity with conscious states, the leap from electrochemical signals to the subjective experience of being. The feeling of seeing the color red, the pang of sadness, the joy of discovery, is a chasm that science is still striving to bridge. This is often referred to as the hard problem of consciousness, and it touches upon the very essence of what it means to be alive and aware. The development of the brain, from a single fertilized cell to the intricate organ capable of abstract thought and complex social interaction, is another area of ongoing fascination. The precise choreography of gene expression, cellular migration, and synaptic pruning that shapes our neural architecture is a marvel of biological engineering, and understanding these processes could hold keys to treating developmental disorders and neurodegenerative diseases. The way our brains wire themselves, adapting and rewiring throughout our lives in response to experience, a phenomenon known as neuroplasticity, is a testament to their dynamic and ever-evolving nature. Yet the full extent and mechanisms of this adaptability are still being explored. Furthermore, the precise ways in which different brain regions communicate and collaborate to produce complex behaviors, emotions, and cognitive functions are not fully understood. We can identify functional connectivity, the patterns of activation between different brain areas, but the underlying language and grammar of this neural dialogue, the subtle interplay of excitation and inhibition, the timing and rhythm of neural firing, are still being meticulously decoded. The sheer interconnectedness means that a change in one area can have ripple effects across the entire network, making it incredibly challenging to isolate the causal factors behind specific functions or dysfunctions. Even the basic building blocks, the neurons themselves, hold secrets. While we understand their general function as electrical and chemical signaling units, the diversity of neuronal types and their specialized roles within complex circuits are still being cataloged and understood. Each type of neuron, with its unique morphology and neurochemical signature, likely plays a specific, yet often subtle, role in the brain's overall operation, contributing to the richness and nuance of our mental lives. The exploration of the brain is a journey into the very core of our being, a scientific quest that is as philosophical as it is biological. It is a field where the most profound questions about ourselves, our existence, and our place in the universe are being actively pursued, not through speculation alone, but through rigorous observation, experimentation, and the relentless pursuit of knowledge. The more we learn, the more we realize how much more there is to discover, a humbling and awe-inspiring realization that underscores the boundless potential of the human mind to understand itself. Within the quiet hum of our own being, an uncharted cosmos unfolds, a testament to the enduring wonder of the mind's own deep and unyielding mysteries. The question of free will persists. We often feel as though we are the captains of our own ships, charting a course through the vast ocean of existence, making choices that genuinely originate from within us. This deeply ingrained sensation of agency, the feeling that we could have chosen differently in any given moment, is what we commonly refer to as free will. It's a cornerstone of our moral and legal systems, forming the very foundation of responsibility and accountability. If our actions are predetermined, then concepts like praise, blame, guilt, and even justice begin to crumble. But when we peer into the intricate workings of the universe, from the subatomic dance of particles to the complex neural networks of our brains, the clear-cut picture of an unconstrained self begins to blur. At the quantum level, the universe seems to operate on probabilities and inherent randomness. Particles don't always behave in predictable ways. Their outcomes are governed by chance until they are observed. This inherent unpredictability at the smallest scales has led some to suggest that perhaps this randomness is the very source of our freedom, injecting an element of true novelty into the causal chain. However, others argue that randomness is not the same as will. A random event is still not something we choose. It simply happens. If our choices are merely the product of random quantum fluctuations in our brains, are we truly free, or just subject to a different, more chaotic form of determinism? Moving up to the macroscopic world, classical physics paints a picture of a deterministic universe. If you know the initial conditions of a system and the laws that govern it, you can, in principle, predict its future state with absolute certainty. Our brains, while incredibly complex, are physical systems made of atoms and molecules that obey these physical laws. Every thought, every decision, every impulse could, in theory, be the inevitable consequence of prior physical states and external stimuli. This is the essence of determinism, the idea that every event, including human cognition, decision, and action, is causally determined by an unbroken chain of prior occurrences. From this perspective, the feeling of making a choice is an illusion, a post hoc rationalization of a process that was already set in motion. Neuroscience adds further layers to this puzzle. Experiments, famously pioneered by Benjamin Libet, have shown that brain activity associated with a decision can be detected before the person is consciously aware of having made that decision. In these studies, participants were asked to press a button whenever they felt the urge to do so, while their brain activity was monitored. The results indicated that a specific brain signal, known as the readiness potential, began to build up in the brain milliseconds to seconds before the participants reported their conscious intention to act. This suggests that our conscious awareness of a decision might be more of a notification of a choice already made by our unconscious brain, rather than the causal origin of that choice. However, these findings are not universally accepted as definitive proof against free will. Critics point to various limitations in the experimental design and interpretation. For instance, the tasks involved are often simple and artificial, not representative of the complex, deliberative decisions we make in everyday life. Furthermore, the interpretation of the readiness potential is debated. It might represent a general preparation for action rather than a specific, predetermined decision. Some neuroscientists propose that consciousness might still play a crucial role, perhaps acting as a veto mechanism, allowing us to consciously inhibit an action that our brain has already prepared. The debate also extends into philosophy, with various schools of thought attempting to reconcile our subjective experience of freedom with the scientific understanding of causality. Compatibilism, for example, argues that free will and determinism are not mutually exclusive. Compatibilists suggest that an action is free if it is caused by the agent's own desires and beliefs, even if those desires and beliefs are themselves determined. In this view, freedom is about acting according to one's own internal states, rather than being coerced or constrained by external forces. Incompatibilists, on the other hand, maintain that if determinism is true, then free will cannot exist, hard determinism. Or if free will exists, then determinism must be false libertarianism. The implications of this question are profound. If we lack free will, how do we assign moral responsibility? Can we truly hold individuals accountable for their actions if those actions were inevitable? This could lead to a radical rethinking of our justice systems, shifting the focus from punishment to rehabilitation and prevention, based on understanding the causal factors that lead to certain behaviors. Conversely, if we do possess genuine free will, then the universe is not a purely mechanistic clockwork, and there is a space for genuine creativity, spontaneity, and personal responsibility that transcends mere physical causation. The very act of questioning our free will might, paradoxically, be an exercise of it. Our capacity for introspection, for self-reflection, and for grappling with abstract concepts like causality and agency suggests a level of cognitive complexity that is at the heart of what we consider to be ourselves. Perhaps the unsolved nature of free will is not a bug in the system, but a feature, a testament to the intricate and perhaps ultimately ineffable nature of consciousness and existence. The question persists, not because we lack the data, but because the very tools we use to investigate our minds are themselves part of the mystery. The persistent echoes of "I could have done otherwise" in the quiet chambers of our minds whisper that perhaps, just perhaps, the universe holds a space for a self that is not entirely bound by the chains of causality, a self that can, in some fundamental way, choose its own path, even amidst the grand, unfolding tapestry of cosmic events. The enigma of aging and immortality. Aging, a process so intimately familiar to every living being, remains one of science's most profound and persistent enigmas. We observe it, we experience it, and for millennia, we have sought to understand and, in some cases, to defy it. But what exactly is asterisk aging? It's not a single disease or a simple wearing out. Instead, it's a complex, multifaceted biological phenomenon, a gradual accumulation of damage and decline at the cellular and molecular level, leading to a reduced ability to maintain homeostasis and an increased susceptibility to disease and death. At its core, aging is a programmed process, etched into our very genetic code, yet its precise mechanisms are still being unraveled. One of the leading theories is the telomere shortening hypothesis. Telomeres are protective caps at the ends of our chromosomes, like the plastic tips on shoelaces. Every time a cell divides, these telomeres get a little shorter. When they become too short, the cell can no longer divide and enters a state called senescence, or cellular aging. Senescent cells don't die. They just stop functioning properly and can even release inflammatory signals that damage surrounding tissues, contributing to the aging process. Another significant factor is the accumulation of cellular damage. Our cells are constantly bombarded by internal and external stressors, from metabolic byproducts like free radicals to environmental toxins. These can damage DNA, proteins, and lipids, impairing cellular function and leading to a gradual decline in tissue and organ performance. The concept of oxidative stress is particularly relevant here, highlighting the damage caused by an imbalance between free radicals and antioxidants in the body. Furthermore, our body's repair mechanisms become less efficient with age. Think of it like a car that, over time, needs more frequent and extensive repairs, and eventually, the cost of maintenance outweighs the car's value. Our cellular machinery for repairing damaged DNA, clearing out waste products, and replacing worn-out components begins to falter. Protein misfolding and aggregation is another area of intense research. Proteins are the workhorses of our cells, and when they misfold, they can lose their function and clump together, forming toxic aggregates that are implicated in neurodegenerative diseases like Alzheimer's and Parkinson's. These aggregates disrupt cellular processes and contribute to the age-related decline in brain function. The concept of stem cell exhaustion also plays a crucial role. Stem cells are the body's raw material, responsible for generating new cells and repairing tissues. With age, the number and function of stem cells decline, diminishing the body's ability to regenerate and repair itself. Imagine a factory with a dwindling supply of skilled workers and a less efficient production line. The cumulative effect of these processes is a systemic decline in physiological function, making us more vulnerable to age-related diseases such as cardiovascular disease, cancer, diabetes, and neurodegeneration. The quest for immortality, or at least significant life extension, is as old as humanity itself, appearing in myths and legends across cultures. While true biological immortality, in the sense of never dying, remains firmly in the realm of science fiction, modern science is making strides in understanding and potentially intervening in the aging process. Research into genetic pathways associated with longevity, such as those involving genes like *DAF2* and DAF16 in worms, or SIRT1* in mammals, offers tantalizing glimpses into the molecular underpinnings of extended lifespan. Therapies aimed at clearing senescent cells, known as senolytics, are showing promise in preclinical studies for improving health span and mitigating age-related conditions. Similarly, interventions that boost cellular repair mechanisms or enhance mitochondrial function are being explored. The study of organisms with exceptional longevity, like certain species of jellyfish that can revert to a polyp stage, or the Greenland shark that can live for centuries, provides valuable insights into the biological strategies for resisting aging. However, the ethical implications of significant life extension are vast and complex, raising questions about overpopulation, resource allocation, and the very definition of a human life. For now, aging remains a fundamental biological constant, a testament to the intricate dance of life and decay, a process that shapes our existence and imbues our finite time with profound meaning. The silent march of years inscribes its story on every cell, a profound reminder that even in our deepest biological mysteries, there is a gentle rhythm to existence. The nature of information in the universe. In the grand tapestry of existence, where stars ignite and galaxies dance, a profound question whispers through the cosmos. What is the fundamental nature of information? We often think of information as something we create, something that resides in books, in digital files, in the very words we speak. But what if information is not merely a product of consciousness, but a foundational element of reality itself? This is one of the most captivating and deeply philosophical unsolved questions in science, one that blurs the lines between physics, philosophy, and even our understanding of consciousness. At its heart, the question of information in the universe probes whether the universe, at its most basic level, can be understood as a computational system. Consider the very fabric of spacetime. Physicists are increasingly exploring the idea that spacetime itself might not be a continuous, smooth entity, but rather a discrete, pixelated structure, much like the pixels on a screen that form an image. If this is the case, then the universe could be seen as a colossal, unimaginably complex computer, processing and storing information. This concept, known as digital physics, suggests that the elementary particles and forces we observe are, in essence, bits of information, the fundamental units of this cosmic computation. This idea has roots in some of the deepest puzzles of modern physics, particularly in the realm of black holes. When matter falls into a black hole, it seems to disappear, taking its information with it. However, a fundamental principle of quantum mechanics is that information can never be truly destroyed. This is known as the information paradox. If information is lost in black holes, it would violate this bedrock principle, suggesting a flaw in our current understanding of physics. Some proposed solutions to this paradox, such as the holographic principle, suggest that all the information about the interior of a black hole, or even the entire universe, could be encoded on its boundary, like a hologram. This implies that information, rather than being contained within a volume, might exist on a surface, a radical departure from our intuitive understanding of space. The implications of this are staggering. If the universe is fundamentally informational, then what we perceive as physical reality could be an emergent property of these underlying informational processes. The laws of physics themselves might be akin to the algorithms running on this cosmic computer. This perspective shifts our understanding from a universe of inert matter and energy interacting through forces to a universe of active, dynamic information processing. Furthermore, the very act of observation in quantum mechanics plays a crucial role in how we understand information. Before an observation, a quantum system can exist in a superposition of states, meaning it embodies multiple possibilities simultaneously. The act of measurement collapses this superposition into a single, definite state, effectively choosing one piece of information from many. This suggests that information is not merely passively stored, but actively participates in shaping reality. The exploration of this question also touches upon the nature of consciousness. If the universe is a computational system, could consciousness itself be an emergent property of complex information processing? This is a question that delves into the hard problem of consciousness, the challenge of explaining how subjective experience arises from physical processes. Some theories propose that consciousness is a form of information processing that is particularly adept at self-referential loops, allowing it to become aware of itself and its environment. The challenge for scientists is to find empirical evidence for these abstract ideas. Experiments in quantum computing and quantum entanglement offer glimpses into the informational nature of reality, demonstrating how information can be manipulated and transferred in ways that seem to defy classical intuition. The search for a theory of everything, a single framework that unifies all the fundamental forces and particles, may ultimately reveal the underlying informational code of the universe. Ultimately, the question of information in the universe is a profound invitation to reconsider our place within it. It suggests that we are not merely passive observers of a physical world, but active participants in a grand cosmic computation. The universe, in this view, is not just a collection of things, but a dynamic, evolving process of information exchange and transformation. It is a universe where the very laws that govern existence might be reducible to the logic of computation, and where the deepest mysteries of reality might be encoded in the language of information. This ongoing quest to understand the informational underpinnings of the cosmos is a testament to the boundless curiosity of the human mind, a journey into the very essence of what it means to be. The universe, in its silent unfolding, may be a grand computation, and we, fleeting moments of awareness within its boundless, informational flow. The limits of computation and artificial intelligence. Our understanding of computation, the very process of calculation and problem-solving that underpins so much of our modern world, is still a frontier of profound inquiry. We marvel at the ever-increasing power of our computers, the sophistication of artificial intelligence, yet there are fundamental boundaries, inherent limitations, to what these systems can achieve. These limits are not merely technological hurdles, soon to be overcome by faster chips or more elegant algorithms. They are, in many cases, theoretical ceilings, dictated by the very nature of mathematics and logic. One of the most significant of these limitations stems from the work of Kurt Gödel, a brilliant logician whose incompleteness theorems, published in the early 20th century, fundamentally reshaped our understanding of formal systems, including computation. Gödel's first incompleteness theorem states that in any consistent formal system, powerful enough to describe the arithmetic of the natural numbers, there will always be true statements that cannot be proven within that system. Imagine a vast library of all possible mathematical truths. Gödel showed that no matter how comprehensive your cataloging system, your formal system, there will always be books, true statements, that are impossible to find using only the rules of your cataloging system. This means that no single computational system, no matter how advanced, can capture all mathematical truths. There will always be truths that lie beyond its provable reach. This has profound implications for artificial intelligence. If an AI is built upon a formal system, then by Gödel's theorem, it cannot, in principle, be capable of proving every true statement about the domain it's designed to understand. This doesn't mean AI is incapable of incredible feats. It simply means there are inherent logical boundaries to its potential knowledge and provability. Think of it as an ultimate ceiling on certainty within a given framework. Another crucial limitation comes from Alan Turing, another giant in the field of computation. Turing's work on the halting problem is foundational. He proved that it is impossible to create a general algorithm that can determine, for any given program and any given input, whether that program will eventually halt, finish its execution, or run forever. This is known as an undecidable problem. It's not that we haven't found the right algorithm yet. It's that such an algorithm cannot exist. This implies that there are problems that no computer, no matter how powerful, can ever solve. We can't even write a program that can reliably tell us which programs are solvable and which will run into an infinite loop. This undecidability has direct consequences for AI. If an AI is tasked with analyzing the behavior of other programs or even its own internal processes, it will inevitably encounter situations where it cannot definitively determine the outcome. This introduces a fundamental uncertainty, a point where the AI must make assumptions or stop its analysis, rather than reaching a guaranteed conclusion. The halting problem underscores that not all questions are algorithmically answerable, and therefore, not all problems are computationally solvable. Beyond these theoretical limits, there are practical constraints. The sheer scale of some computational problems can be overwhelming. The P versus NP problem, one of the most important unsolved problems in computer science, asks whether every problem whose solution can be quickly verified, NP problems, can also be quickly solved, P problems. Most computer scientists believe that P is not equal to NP, meaning there are problems that are computationally intractable, meaning the time required to solve them grows exponentially with the size of the input. For such problems, even with the fastest supercomputers, solving them for even moderately sized inputs would take longer than the age of the universe. This makes certain types of optimization, cryptography, and scientific modeling inherently difficult, if not impossible, to achieve with perfect efficiency. Furthermore, the physical limits of computation are also being explored. As we push the boundaries of miniaturization and speed, we encounter quantum effects and energy dissipation that pose significant challenges. At the atomic scale, quantum mechanics introduces inherent probabilistic behavior and the potential for errors that are difficult to control. The energy required to perform computations also becomes a limiting factor. The universe has a finite energy budget. The development of artificial intelligence, while breathtaking in its progress, is also bound by these computational and logical limits. While AI can learn, adapt, and even exhibit creativity within its defined parameters, it cannot transcend the fundamental rules of computation and logic that govern its existence. The quest for artificial general intelligence, an AI that can perform any intellectual task a human can, is not necessarily impossible, but it might require entirely new paradigms of computation, or a deeper understanding of consciousness itself, which remains one of science's greatest unsolved mysteries. The very definition of intelligence and understanding becomes blurred when we consider the inherent limitations of any formal system. The pursuit of ever more powerful computation and sophisticated AI is a journey into the heart of what it means to process information, to solve problems, and to understand the universe. Yet, these explorations inevitably lead us to the edge of what is knowable and solvable, revealing a landscape of inherent limits, not as failures, but as profound characteristics of the cosmos and the systems we create within it. And so, even as we chart the vast territories of computation and artificial intelligence, we are reminded that the universe holds secrets that may forever lie just beyond our computational reach. A gentle whisper that some truths are best contemplated rather than definitively proven, allowing a quiet wonder to fill the spaces where certainty cannot tread. The role of chaos in a seemingly ordered universe. We often perceive the universe as a grand, clockwork mechanism, ticking along with predictable precision. From the orbits of planets to the predictable cycles of seasons, order seems to be the fundamental principle governing existence. Yet, beneath this veneer of serene predictability lies a profound and often counterintuitive truth. Chaos is not an anomaly, it is an intrinsic, and indeed, a creative force within this seemingly ordered cosmos. The study of chaos theory, a branch of mathematics and physics, reveals that even in systems governed by deterministic laws, small, seemingly insignificant changes can lead to vastly different and unpredictable outcomes over time. This phenomenon, known as the butterfly effect, illustrates how the flap of a butterfly's wings in Brazil could, in theory, set off a tornado in Texas weeks later. It's not that the system is random. It's that our ability to predict its long-term behavior is fundamentally limited by the extreme sensitivity to initial conditions. Consider the weather, a classic example of a chaotic system. We can accurately predict the weather for a few days, but beyond that, our predictions become increasingly unreliable. This isn't due to a lack of sophisticated models or powerful computers. It's inherent to the nature of atmospheric dynamics. Tiny variations in temperature, pressure, or wind speed, too small for us to even measure, can amplify over days and weeks, leading to entirely different weather patterns. This doesn't mean weather is random. It means it is deterministic but practically unpredictable in the long term. This principle extends far beyond meteorology. In economics, small market fluctuations can trigger massive booms or busts. In biology, the intricate dance of ecosystems, the evolution of species, and even the development of an embryo are all influenced by chaotic dynamics. A slight genetic mutation, a subtle environmental shift, can set a lineage on a completely different evolutionary path. The complex patterns of blood flow through our veins, the firing of neurons in our brains, the very rhythm of our heartbeats. These are all examples of systems that operate on the edge of chaos, exhibiting a dynamic balance between order and unpredictability. This edge of chaos is often where the most interesting and adaptive behaviors emerge. In living organisms, a certain degree of chaos allows for flexibility and resilience. It enables them to adapt to changing environments, to find novel solutions to problems, and to evolve. Too much order can lead to rigidity and fragility, while too much chaos can lead to collapse. It is this delicate balance, this dynamic interplay between predictable patterns and unpredictable fluctuations, that allows for complexity, creativity, and ultimately, the rich tapestry of life we observe. Chaos theory doesn't negate the laws of physics. Instead, It provides a deeper understanding of how these laws can manifest in complex, emergent behaviors. It shows us that the universe is not a simple, static machine, but a dynamic, evolving entity. It suggests that even within a deterministic framework, there is room for novelty, for surprise, and for a profound sense of wonder at the intricate unfolding of reality. The order we perceive is often the result of underlying chaotic processes finding temporary, stable patterns, only to be disrupted and reformed in new and unexpected ways. This inherent unpredictability is not a flaw, but a feature, a testament to the universe's ceaseless capacity for creation and transformation. It is this very element of the unpredictable that fuels innovation, adaptation, and the continuous exploration of possibilities, making the universe not just ordered, but vibrantly alive. And in this dance of predictable patterns and unpredictable turns, we find a profound reflection of our own lives, where the grandest designs can emerge from the smallest, unseen shifts, reminding us that even in apparent disorder, a deeper, more dynamic order unfolds. The unseen forces shaping our world. We often perceive the world around us as a collection of solid objects, governed by clear, visible interactions. We see a ball fall, a car move, a planet orbit. These are the manifestations of forces we can readily observe and to a degree understand. Yet beneath this apparent solidity and predictable motion lies a universe sculpted by forces that are, for the most part, invisible, intangible, and profoundly influential. These unseen forces are not merely abstract concepts. They are the architects of our reality, from the subatomic dance of particles to the grand ballet of galaxies. Consider, for instance, the electromagnetic force. It is responsible for the light that illuminates our world, the electricity that powers our civilizations, and the very chemical bonds that hold atoms together, forming the molecules of life. Without electromagnetism, there would be no chemistry, no biology, no matter as we know it. It is a force that can be both gentle, as in the subtle attraction between oppositely charged ions, and immensely powerful, as in a lightning strike or the magnetic fields that shield our planet from harmful solar radiation. This force operates across vast distances, its influence diminishing with the square of the distance, yet its reach is truly cosmic. Then there are the nuclear forces. The strong nuclear force, paradoxically, is the strongest force in the universe, but it acts only over incredibly short distances, binding protons and neutrons together within the nucleus of an atom. It is this force that prevents the positively charged protons from repelling each other and tearing the nucleus apart. Without the strong nuclear force, the very existence of atoms beyond hydrogen would be impossible, and thus, the universe as we know it would not exist. Its immense power is also the source of the energy released in nuclear reactions, powering stars and on Earth, harnessed in nuclear power plants. Conversely, the weak nuclear force, though weaker than the strong force and electromagnetism, plays a crucial role in radioactive decay and certain nuclear fusion processes, like those that occur in the Sun. It is responsible for transforming one type of subatomic particle into another, a fundamental process in the ongoing evolution of matter in the cosmos. These fundamental forces, electromagnetism and the nuclear forces, are the bedrock of matter and energy, but their influence extends far beyond the atomic realm. They dictate how stars are born, how they evolve, and how they eventually die, scattering the elements forged within them across the vastness of space, elements that then become the building blocks for new worlds and indeed for ourselves. The very structure of the universe, the vast cosmic web of galaxies and clusters, is influenced by these forces, though on larger scales, gravity emerges as the dominant player. Gravity, while often perceived as a force of attraction between massive objects, is, in fact, a curvature of spacetime itself, as described by Einstein's theory of general relativity. It is gravity that holds us to the Earth, keeps the Moon in orbit around our planet, and orchestrates the majestic dance of galaxies. It is a force that, though seemingly weak at the atomic level, becomes overwhelmingly powerful when dealing with astronomical masses, shaping the very fabric of the cosmos. And then there are the more speculative, yet equally profound, unseen forces. Concepts like dark matter and dark energy, which together are thought to constitute about 95% of the universe's total mass energy content, are placeholders for forces and substances we cannot directly detect with current instruments. Dark matter, for example, exerts a gravitational pull that influences the rotation of galaxies and the motion of galaxy clusters, suggesting the presence of a vast, invisible scaffolding holding the universe together. Dark energy, on the other hand, appears to be driving the accelerated expansion of the universe, pushing galaxies further apart at an ever-increasing rate. These are not just theoretical curiosities, they are fundamental components of our universe, whose true nature remains one of science's most compelling mysteries. The implications of these unseen forces are staggering. They remind us that our everyday experience, while rich and complex, is but a thin veneer over a universe governed by principles that are often subtle, hidden, and far beyond our immediate sensory grasp. To contemplate these unseen forces is to confront the limits of our perception and to acknowledge the vastness of what we do not yet understand. It is a humbling, yet exhilarating, realization that the world we inhabit is far more intricate and mysterious than it appears, a constant testament to the profound and subtle workings of the cosmos. The universe whispers its secrets through forces we cannot see, weaving the tapestry of existence with invisible threads of energy and influence. The ultimate fate of all knowledge. We stand at a precipice, gazing into the vast expanse of what we know, and more profoundly, what we do not. The pursuit of knowledge is an inherently human endeavor, a relentless drive to understand the universe and our place within it. From the earliest cave paintings to the most complex algorithms governing our digital world, humanity has meticulously gathered, categorized, and built upon its understanding. Yet as our knowledge grows, so too does the awareness of its potential impermanence. Consider the grand libraries of antiquity, repositories of wisdom that have, for the most part, crumbled to dust. The Library of Alexandria, a beacon of learning, a symbol of accumulated human thought, is now a poignant reminder of how easily knowledge can be lost. Fires, wars, neglect, these are the silent, often brutal, agents of oblivion. But the fate of knowledge is not solely a tale of physical destruction. There are more subtle, yet equally powerful, forces at play. As scientific paradigms shift, older theories, once considered immutable truths, are relegated to the footnotes of history. The geocentric model of the solar system, once the bedrock of astronomical understanding for millennia, was eventually superseded by the heliocentric view. The knowledge itself wasn't destroyed, but its primacy, its absolute truth, was dissolved. Imagine future civilizations, or even future iterations of our own, looking back at our current understanding of quantum mechanics or cosmology. Will they find our theories quaint, incomplete, or perhaps even fundamentally flawed? The very act of acquiring knowledge can, in a sense, render previous knowledge obsolete, not because it was wrong, but because it was a stepping stone to a deeper, more nuanced understanding. Then there is the challenge of information decay in the digital age. We meticulously store vast amounts of data on servers in the cloud on hard drives. But what is the long-term viability of these formats? Will the technologies we use today be readable, accessible in 1,000 or even 100 years. The rapid obsolescence of hardware and software presents a unique and unprecedented threat to the permanence of our digital heritage. Data rot, file corruption, the sheer volume of information making it difficult to curate and preserve. These are the modern-day equivalents of the fires that consumed ancient scrolls. We are, in a way, creating a vast, ephemeral archive, a testament to our current capabilities but a potential enigma for those who come after. Furthermore, consider the very nature of understanding. Knowledge is not static. It is dynamic, evolving, and often interpreted. What one generation considers a fundamental truth, another might see as a metaphor, a philosophical construct, or even a myth. The meaning we ascribe to our discoveries can shift and transform over time, altering the very essence of what we believe we know. The ultimate fate of knowledge, then, is not a singular event, but a continuous process of transformation, loss, and rediscovery. It is a cosmic dance between creation and entropy, between the light of understanding and the shadows of forgetting. Even the most profound scientific discoveries, the most elegant philosophical insights, are subject to the grand unfolding of time. They are precious, fleeting sparks in the immense darkness, each contributing to the ever-changing tapestry of existence. The universe itself is a grand experiment, and the knowledge we glean from it is but a temporary annotation in its boundless narrative. And so, the accumulated wisdom of ages may, in the grandest of cosmic scales, eventually fade, like whispers on the wind, reminding us that even our most profound insights are but transient echoes in the silent, eternal expanse. The enduring wonder of the unknown. The vast expanse of scientific inquiry, while illuminating countless corners of existence, also serves to highlight the sheer, breathtaking immensity of what remains undiscovered. It's a humbling realization, this continuous unveiling of deeper mysteries, a testament to the fact that our current understanding is but a single, flickering candle in an infinite, star-dusted darkness. Think of it as standing on the shore of an ocean, having mapped only a few shallow inlets, while the true depths, teeming with unimagined life and landscapes, stretch out beyond the horizon of our current perception. Each answered question, rather than closing a door, often opens a dozen more, each beckoning with the promise of profound revelation. This isn't a cause for despair, but rather the very essence of wonder. The universe, in its infinite complexity, offers us a perpetual invitation to explore, to question, to dream. It's in the spaces between what we know that the most profound questions reside, the ones that spark our curiosity and drive our relentless pursuit of knowledge. Consider the very act of scientific discovery. It is a process of venturing into the unknown, of piecing together fragments of truth from the vast tapestry of ignorance. The unknown is not a void to be feared, but a fertile ground for imagination, a canvas upon which we can project our deepest hopes and most ambitious inquiries. It is the fertile soil from which all future breakthroughs will grow. The very fact that there are limits to our current knowledge is what makes existence so endlessly fascinating. If we knew everything, if every question had a definitive answer, the universe might, paradoxically, become a less wondrous place. The thrill of the chase, the intellectual pursuit, the sheer joy of a new insight, these are all born from the presence of the unknown. It is the unknown that fuels our creativity, that inspires our art, our philosophy, and our science. It is the unknown that reminds us of our place in the grand cosmic narrative, not as masters of all knowledge, but as humble, curious travelers on an extraordinary journey. The greatest discoveries often arise not from a desire to confirm what we already believe, but from a willingness to confront the perplexing, the anomalous, the utterly unexpected. These are the moments when science truly shines, when our understanding is stretched and redefined. The ongoing quest for knowledge is not about conquering the unknown, but about learning to dance with it, to appreciate its profound beauty and its intrinsic value. The unknown is the wellspring of all possibility, the silent promise of future marvels yet to be conceived. It is the very essence of the ongoing, unfolding story of the cosmos, a story in which we are both participants and storytellers. This enduring sense of mystery, this profound appreciation for the vastness of what we do not yet comprehend, is the ultimate fuel for the human spirit, a constant reminder of the infinite potential that lies both within us and all around us. The unknown is not an ending, but a perpetual, glorious beginning. It is the silent, majestic hum of creation, forever inviting us to listen, to learn, and to wonder. The more we learn, the more we realize how much more there is to explore, creating a beautiful, infinite loop of curiosity. This ceaseless unfolding is the universe's greatest gift to the seeking mind, a constant source of awe and a gentle reminder that the journey of understanding is as profound and as beautiful as any destination. It is the unknown that keeps the flame of inquiry burning brightly, ensuring that the pursuit of knowledge will continue, not as an obligation, but as an act of profound, joyful exploration for all time. The unknown is the ultimate frontier, and the wonder it inspires is the very engine of our evolution. It is the quiet promise of tomorrow's revelations, waiting patiently for us to discover them. In the grand theater of existence, the unknown is not a silence to be filled, but a resonant echo that reminds us of the infinite beauty of our journey. Our calm exploration has covered the vast expanse of the universe, delving into its most profound and persistent enigmas. We've drifted through the perplexing nature of dark matter and dark energy, the mind-bending principles of quantum mechanics, and the enduring question of whether we are truly alone. We've considered the very fabric of time, the elusive nature of consciousness, and the ultimate fate of all things. Tonight, we have reviewed the principles of scientific inquiry, not as a race for definitive answers, but as a gentle, continuous journey of curiosity and wonder. These unanswered questions, these vast unknowns, are not sources of frustration, but rather invitations to peace. They remind us that the universe is far grander, far more complex, and far more mysterious than our current understanding can encompass. This perspective, this quiet acknowledgement of the immense unknown, can be a profound source of comfort. It frees us from the burden of needing to know everything, allowing us instead to simply be, to simply exist within this magnificent, unfolding mystery. Your own existence, like the cosmos itself, is a tapestry woven with threads of both the known and the unknown. The anxieties that may have kept you awake are but fleeting patterns within this grander design. Allow the vastness of these cosmic questions to gently dissolve your immediate worries, to expand your perspective beyond the confines of your immediate distress. The universe does not demand answers from you. It simply invites you to witness its breathtaking, unsolved beauty. It is time to rest now. Allow the quiet wonder of the universe to embrace you. Let the unresolved mysteries lull you into a state of peaceful surrender. Sleep well. Good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now, continuing this gentle exploration into the heart of the unknown.